Imagine a universe governed by two wildly successful, yet fundamentally contradictory sets of rules. On one hand, we have Albert Einstein's general relativity, a beautiful, almost poetic description of gravity, picturing it not as a force but as the very fabric of space and time, warped and curved by mass and energy. Think of it like a bowling ball placed on a trampoline, creating a dip that pulls in nearby objects. This is Einstein's universe. Elegant, predictable, and supremely accurate when describing the movements of planets, the bending of light around massive stars, and even the expansion of the cosmos itself. Then, there's the quantum world, a realm of bizarre probabilities, where particles can be in multiple places at once, connected by spooky, instantaneous links across vast distances. Governed by quantum mechanics, this is the realm of atoms and subatomic particles, a world where uncertainty reigns supreme. Measurement itself alters reality, and everything is a blur of probabilities rather than concrete certainties. Quantum mechanics has allowed us to build lasers, computers, and understand the very structure of matter. It's an undeniably successful theory. But here's the rub, the cosmic conflict at the heart of modern physics. These two descriptions of the universe, each incredibly successful in its own domain, simply do not play well together. It's like trying to build a house with blueprints from two different architects, one designing in elegant curves and the other in sharp, jagged angles. Eventually, the structure will crumble. Where does this incompatibility manifest most dramatically? In the most extreme cosmic environments. Think about the heart of a black hole, where gravity is so intense that it crushes matter to infinite density, or consider the very first moments of the universe, the Big Bang, a singularity of unimaginable energy and compression. In these scenarios, both gravity and quantum effects are pushed to their limits. Apply both general relativity and quantum mechanics at the same time, and the mathematics breaks down. Equations spew out infinities, paradoxes arise, and our understanding of the universe collapses. It's as if nature is throwing us a gigantic curveball saying your current understanding is incomplete. We have two theories that work brilliantly in most situations, but when the stakes are highest, when we peer into the universe's most extreme corners, they fail us. We need a new theory, a theory of quantum gravity, to reconcile these two giants of physics. This is not just a matter of tidying up loose ends, it is about understanding the fundamental nature of reality itself. The quest to find this elusive theory is perhaps the greatest challenge facing physicists today, a grand unification quest to weave together the smooth fabric of Einstein's cosmos with the fuzzy, probabilistic rules of the quantum world. A quest that promises to revolutionize our understanding of everything. So, we find ourselves at a crossroads. Two towering achievements of the human intellect, general relativity and quantum mechanics, stand in stark opposition when pushed to their limits. It's a cosmic puzzle demanding a solution. But before we can even begin to contemplate weaving these disparate threads together, we must first understand the sheer audacity, the breathtaking elegance of Einstein's theory of general relativity. Forget everything you think you know about gravity as a simple force, like the pull of a magnet. Einstein turned this entire concept on its head. Imagine, if you will, space-time itself as a boundless ocean. Now picture Earth as a great ship sailing through that ocean. As the ship moves, it creates ripples and waves, distorting the water around it. This is, in essence, what massive objects do to space-time. They warp and curve it. Gravity, therefore, isn't a force pulling you down, but rather it's the curvature of space-time directing your path. Think of a marble rolling around a funnel. It circles inward not because something is tugging it, but because the funnel's shape dictates its trajectory. This warped geometry is what we perceive as gravity. This revolutionary idea, unveiled in 1915, immediately shattered the foundations of Newtonian physics. It wasn't just a tweak to the old theory, it was a complete paradigm shift. And the predictions that sprung forth from this new understanding were nothing short of mind-bending. Consider black holes, those cosmic vacuum cleaners with gravity so intense that not even light can escape. They were a direct consequence of Einstein's equations, initially dismissed as mathematical curiosities. Yet, decades later, astronomical observations confirmed their existence, revealing them as powerful engines at the heart of galaxies, capable of devouring entire stars. Then there are gravitational waves, ripples in space-time predicted to propagate at the speed of light. For decades, they remained elusive, a theoretical whisper on the edge of detection. But in 2016, over a century after Einstein's prediction, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the faint chirp of two black holes colliding over 1 billion light-years away. It was a monumental achievement, a direct confirmation of Einstein's theory and a brand new window into the universe, allowing us to see cosmic events that are invisible to traditional telescopes. Picture the universe as a vast orchestra, with gravitational waves as the silent music emanating from its most cataclysmic events. General relativity has proven astonishingly accurate, explaining everything from the subtle precession of Mercury's orbit to the large-scale structure of the cosmos. It's the cornerstone of our understanding of the universe at its grandest scales. It allows us to model the evolution of galaxies, understand the expansion of the universe, and even peer back to the very first moments after the Big Bang. It seems, at first glance, to be an almost perfect theory. So if Einstein's vision is so compelling, so thoroughly validated by observation, why are we still searching for something more? Why do we need quantum gravity? The answer, as we'll discover, lies in those very same extreme environments where general relativity shines brightest. Places where the fabric of space-time is stretched to its breaking point. Places where the seemingly immutable laws of physics begin to unravel. In those extreme regions, the elegant certainty of Einstein's universe collides head-on with the fuzzy, uncertain world of quantum mechanics, and that is where the real mystery begins. So while Einstein's general relativity paints a picture of a smooth, predictable universe at large scales, a completely different drama unfolds when we zoom into the realm of the incredibly small. Forget the graceful curves of spacetime. We're diving headfirst into a world of fuzzy probabilities where the very act of observation changes reality. This is the quantum realm, governed by the bizarre and often counterintuitive laws of quantum mechanics. Have you ever considered that the chair you're sitting on, the device you're watching this on, even you yourself, are composed of particles that, at their most fundamental level, don't really have a definite location until you look at them? It sounds like science fiction, but it's the bedrock of quantum theory. Imagine a tiny electron, not as a miniature ball orbiting an atom, but as a cloud of possibilities, existing in multiple places simultaneously. This is known as superposition. It's only when we attempt to pinpoint its location that the electron chooses a single spot, collapsing its wave function and revealing its position. It's like a cosmic game of hide-and-seek, where the rules change the moment you start searching. This inherent uncertainty is enshrined in what's known as the Heisenberg uncertainty principle, formulated by the brilliant German physicist Werner Heisenberg in 1927. The principle states that we can never know both the position and the momentum of a particle with perfect accuracy. The more precisely we know one, the less precisely we can know the other. It's not a limitation of our instruments. It's a fundamental property of the universe. Think of it like trying to catch a water droplet. The harder you squeeze, the more it slips through your fingers. But the quantum weirdness doesn't stop there. Enter quantum entanglement, a phenomenon so bizarre that even Einstein famously called it spooky action at a distance. Imagine two entangled particles linked in such a way that they share the same fate, no matter how far apart they are. Measure the property of one particle and you instantly know the property of the other, even if they are light years away. It's as if they are communicating instantaneously, defying the cosmic speed limit set by Einstein himself. While the exact mechanism behind entanglement is still debated, it has been experimentally verified countless times and is even being harnessed for cutting-edge technologies like quantum computing and quantum cryptography. Despite its strangeness, quantum mechanics is not just a theoretical curiosity. It's arguably the most successful theory in the history of science. It underpins our understanding of everything from the behavior of atoms and molecules to the structure of the nucleus, the engine of stars, and the very existence of life itself. It has given us lasers, transistors, nuclear power, medical imaging, and countless other technological marvels that define our modern world. Without quantum mechanics, none of this would be possible. Consider the digital revolution. The chips that power our computers, smartphones, and countless other devices rely on the quantum mechanical behavior of electrons in semiconductors. The laser scanners at supermarket checkouts, the MRI machines in hospitals, and the GPS satellites orbiting our planet all depend on the precise control and manipulation of quantum phenomena. It's a testament to the power of human ingenuity that we have managed to harness the most bizarre aspects of nature to create technologies that would have been unimaginable just a century ago. Yet, even with its unparalleled success, quantum mechanics leaves us with profound questions. What does it really mean for a particle to exist in multiple states at once? Does the act of observation truly create reality? And how can we reconcile the probabilistic, uncertain world of the quantum with the deterministic, geometric world of general relativity? These questions lie at the heart of the quest for quantum gravity, a quest to unify the two most successful and yet fundamentally incompatible theories in physics. The journey promises to take us to the very edge of human knowledge, to the Planck scale, where space and time themselves may dissolve into a frothing sea of quantum foam, where the familiar laws of physics break down and the true nature of reality lies hidden, waiting to be unveiled. Even as we marvel at the separate triumphs of general relativity and quantum mechanics, a nagging question persists. What happens when these two titans of physics clash? Where do their descriptions of reality break down, revealing the cracks in our current understanding? The answer, it turns out, lies in the universe's most extreme environments. Think of them as cosmic proving grounds, where the laws of physics are pushed to their absolute limits. These are the places where gravity is unimaginably strong, where quantum effects are amplified to macroscopic scales, and where the very fabric of spacetime is stretched, twisted, and perhaps even torn. Perhaps the most obvious example is the heart of a black hole. Imagine a star many times more massive than our sun collapsing under its own gravity. As it shrinks, the gravitational pull intensifies, warping spacetime to an extreme degree. Eventually, all the star's mass is compressed into an infinitely small point called a singularity. According to general relativity, this singularity is a place of infinite density, where space-time ceases to exist. But that's precisely where the problems begin. Infinite density means infinite curvature, infinite energy, and infinite everything else. It's a mathematical nightmare, a clear sign that our current theory is breaking down, and that is not all. The quantum world also plays a part in this drama. What happens to all the quantum information that falls into a black hole? Does it simply disappear, violating one of the fundamental principles of quantum mechanics? Or is there some subtle quantum process that preserves this information, perhaps encoded in the black hole's surface area like a holographic projection? This is the information paradox, a profound puzzle that has vexed physicists for decades, and it highlights the deep conflict between general relativity and quantum mechanics. But black holes aren't the only cosmic arenas where these giants collide. Consider the very first moments of the universe, the Big Bang. According to our best cosmological models, the universe began as an incredibly hot, dense state, far smaller than even a single atom. In this primordial soup, gravity and quantum effects would have been equally important, shaping the very structure of space-time. Describing the Big Bang requires a theory that can handle both gravity and quantum mechanics simultaneously, but our current theories fail miserably. Apply the equations of general relativity to the Big Bang, and you will end up with yet another singularity, a moment of infinite density and temperature where the laws of physics simply break down. It's like trying to run a car engine at 10,000 revolutions per minute. Eventually, something is going to explode. In the case of the Big Bang, that explosion is the breakdown of our theoretical framework. We need a new engine, a new theory of quantum gravity to understand what happened in those fleeting moments after the universe's birth. These extreme environments, the heart of black holes, and the first moments of the Big Bang represent the ultimate testing grounds for our understanding of the universe. They are the places where the familiar laws of physics crumble, revealing the need for something deeper, something more fundamental. These cosmic frontiers show why a new theory, quantum gravity, is desperately needed, for until we have such a theory, we are like explorers standing at the edge of a vast uncharted territory, armed with incomplete maps and unreliable compasses. The mysteries of the cosmos beckon, and the quest to unlock them will require us to push the boundaries of human knowledge, to challenge our deepest assumptions, and to dare to imagine a universe far stranger and more wonderful than we ever thought possible. And the path forward may require entirely new ideas, concepts so revolutionary that they will make even Einstein and Planck blush. The journey is sure to be challenging, but the potential rewards are immense. What awaits us on the other side of this scientific revolution may be a profound new understanding of reality itself. What if our view of the universe is just a glimpse of the truth and something more incredible is coming soon? But how do we even begin to bridge this chasm between the infinitely large and the infinitesimally small? Where do we even start to look for a theory of quantum gravity? The answer, perhaps surprisingly, lies in confronting the ultimate frontier of nature itself, the Planck scale. But what exactly is the Planck scale, and why does it hold the key to unlocking the secrets of the universe? Think of it as the theoretical basement of reality, the smallest possible length and the shortest possible time that have any physical meaning. It is a realm so tiny, so energetic, that our current understanding of space and time simply breaks down. To get a sense of just how small we are talking, imagine shrinking yourself down, not just to the size of an ant or even an atom, but far, far smaller. Imagine shrinking down past the subatomic particles, past the quarks and leptons, past anything we can currently detect with our most powerful microscopes. To reach the Planck length, you would need to shrink yourself down to approximately 1.6 times 10 to the power of minus 35 meters. That is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 large as a galaxy. Now, consider the Planck time, the shortest unit of time that has any meaning in our universe. It is the time it would take for light to travel the Planck length, an incomprehensibly brief instant of approximately 5.4 times 10 to the power of minus 44 seconds. That's
0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000ooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooooo experiment, what a single atom is to the entire observable universe. At this scale, our familiar notions of space and time begin to dissolve.
The smooth, continuous fabric of spacetime, as described by Einstein, gives way to something far more bizarre, a seething foam of quantum fluctuations. Imagine the surface of the ocean, calm and serene from a distance, but up close, a turbulent chaos of waves and foam. This is a loose analogy to what physicists believe space-time might look like at the Planck scale, a quantum foam, where virtual particles and microscopic wormholes are constantly popping in and out of existence. It's a place where the very structure of reality becomes probabilistic, where cause and effect blur, and where the laws of physics, as we know them, may no longer apply. It is a realm of unimaginable energies, far exceeding anything we can create in our most powerful particle colliders. To probe the Planck scale directly, we would need a particle accelerator the size of our galaxy, a feat that is, to put it mildly, beyond our current technological capabilities. This is why the Planck scale represents the ultimate challenge for physicists. It is a frontier that seems almost impossible to reach, a realm governed by physics that we do not yet understand. Yet, it is also the key to unlocking the secrets of quantum gravity, the theory that will finally reconcile Einstein's elegant universe with the bizarre world of quantum mechanics. But if we cannot directly probe the Planck scale with experiments, how can we ever hope to understand it? The answer lies in looking for indirect clues, subtle hints that might reveal the nature of quantum gravity. Perhaps the faint afterglow of the Big Bang, or the behavior of black holes, or even the very structure of space-time itself might hold the key. It's a bit like trying to understand the workings of a clock by examining its shadow. You can't see the gears and springs directly, but the shadow might reveal something about the clock's inner mechanisms. The quest to understand the Planck scale is not just about filling in the gaps in our knowledge, it's about transforming our fundamental understanding of reality. It's about grappling with the deepest questions about the nature of space, time, and the universe itself. What if space and time are not fundamental, but emerge from something more basic? What if our universe is just one of countless others, each governed by different laws of physics? These are the mind-bending questions that arise when we dare to venture into the quantum realm. The challenge is immense, but the potential rewards are even greater. For if we can unlock the secrets of the Planck scale, we will finally be able to answer the ultimate question: what is the true nature of reality? Could it be that there are dimensions beyond our perception that are hidden from us, or that space and time are not as continuous as we think? And how can we test these theories if even reaching the tiniest fraction of this scale is still a distant reality? So, we find ourselves peering into the abyss, a realm of unimaginable energy and incomprehensible smallness, a place where the very fabric of reality seems to dissolve into a chaotic foam. But what if, hidden within that quantum froth, lie the seeds of our entire universe? What if the answers to the deepest mysteries of quantum gravity are whispered to us from the very beginning of time? Imagine traveling back 13.8 billion years, not in some fantastical time machine, but in the minds of the scientists who are tirelessly piecing together the puzzle of our cosmic origins. We arrive at the Big Bang, not as a cataclysmic explosion in empty space, but as the very birth of space and time themselves. A moment of unimaginable density and temperature, a singularity where the known laws of physics simply cease to apply. It is here, in this crucible of creation, that gravity and quantum mechanics were inextricably intertwined, shaping the destiny of the cosmos. But how can we possibly hope to understand what happened in those first fleeting moments? The energies involved are far beyond anything we can recreate in a laboratory. The conditions are so extreme that even our most sophisticated theories break down. It's like trying to understand the intricate workings of a Swiss watch by smashing it with a hammer. We need a different approach, a way to listen for the faint echoes of the Big Bang, to decipher the whispers from the beginning. And that's where the cosmic microwave background comes in. Imagine the universe as a giant oven, and the Big Bang as the moment it was switched on. As the universe expanded and cooled, the primordial plasma gradually became transparent, releasing a flood of radiation that has been traveling through space ever since. This is the cosmic microwave background, or CMB, the afterglow of the Big Bang. It's like a baby picture of the universe taken when it was only 380,000 years old. Now the CMB is remarkably uniform, a testament to the incredible homogeneity of the early universe. But it's not perfectly smooth. There are tiny fluctuations, minute variations in temperature that represent the seeds of all the structures we see today. Galaxies, clusters of galaxies, and the vast cosmic web that spans the observable universe. These fluctuations are like fingerprints, subtle clues about the conditions that prevailed in the very early universe. And by studying them, scientists hope to learn about the physics that governed the Big Bang, including the elusive theory of quantum gravity. But how did these fluctuations arise in the first place? The leading theory is something called inflation, a period of incredibly rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. Imagine the universe inflating like a balloon, expanding exponentially in a minuscule amount of time. According to inflation theory, quantum fluctuations, those random jitters in the quantum foam, were stretched and amplified during this period of rapid expansion, transforming them from microscopic ripples into the macroscopic seeds of cosmic structure. It's a mind-bending idea, the notion that the largest structures in the universe originated from the smallest quantum fluctuations. It's like saying that Mount Everest began as a tiny ripple on a pond. But it explains many of the observed properties of the cosmic microwave background, including its uniformity and its spectrum of fluctuations. If inflation is correct, then the cosmic microwave background is not just a baby picture of the universe, it's a snapshot of quantum gravity in action. But proving inflation is no easy task. The signals we are looking for are incredibly faint, buried beneath layers of noise and foreground contamination. It's like trying to hear a whisper in a hurricane. Scientists are using incredibly sensitive telescopes, both on the ground and in space, to map the cosmic microwave background with unprecedented precision, searching for subtle patterns that might reveal the telltale signs of inflation. One such pattern is something called B modes, a swirling polarization pattern in the cosmic microwave background that could be a direct signature of primordial gravitational waves generated during inflation. Detecting these B modes would be a monumental achievement, providing strong evidence for inflation and opening a new window into the quantum gravity era. It would be like catching a glimpse of the universe's birth certificate, confirming that our cosmos originated from a quantum seed. The hunt is on, and the stakes are high. For if we can unlock the secrets of the cosmic microwave background, we may finally be able to answer the ultimate question: where did we come from, and what is our place in the universe? And perhaps in that quest we'll catch a fleeting glimpse of something even more profound, a whisper of the quantum gravity theory that birthed it all. But the CMB might not be the only relic of the early universe that can reveal secrets about quantum gravity. What about those cosmic vacuum cleaners, those inescapable prisons of gravity that lurk in the darkest corners of the cosmos, black holes? Imagine an object so dense that even light, the fastest thing in the universe, cannot escape its clutches. These are black holes, and they represent a unique intersection of general relativity and quantum mechanics. Are they truly the ultimate destroyers, or do they hold a key to a deeper understanding of the universe? Black holes have captivated scientists and the public alike for decades. Their very existence seems to defy common sense. How can something be so massive, so compact, that it creates a region of space-time from which nothing can return? The answer, as we've touched on before, lies in Einstein's theory of general relativity. When a massive star exhausts its nuclear fuel, it can no longer support itself against the relentless force of gravity. The star collapses inward, crushing its core to an unimaginable density. As the star shrinks, the curvature of space-time around it intensifies, creating a kind of gravitational whirlpool that sucks in everything nearby. Eventually, the star collapses into a point of infinite density called a singularity, surrounded by a region called the event horizon. The event horizon is the point of no return. Once something crosses the event horizon, it is forever lost to the outside universe. Not even light can escape, hence the name black hole. From the outside, a black hole appears as a perfectly black sphere, a void in space-time. But what happens inside the event horizon? What happens to all the matter and energy that falls into the black hole? According to general relativity, it is all crushed into the singularity, a point of infinite density where the laws of physics, as we know them, cease to exist. This singularity is a major problem for physicists. Infinities are generally a sign that our theories are breaking down. It's like dividing by zero in mathematics. You end up with a nonsensical answer. But here's where things get even more interesting. In the 1970s, the brilliant British physicist Stephen Hawking made a groundbreaking discovery that would forever change our understanding of black holes. Hawking realized that quantum mechanics, the theory governing the behavior of particles at the subatomic level, has something to say about black holes. He showed that black holes are not entirely black. Instead, they emit a faint glow of radiation, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon. Virtual particles, which are constantly popping in and out of existence in the quantum world, can sometimes be separated by the event horizon. One particle falls into the black hole, while the other escapes into space as Hawking radiation. Hawking radiation is extremely faint, but it has profound implications. It means that black holes are not eternal. They slowly evaporate over time, losing mass and energy through the emission of Hawking radiation. The smaller the black hole, the faster it evaporates. Eventually, a black hole will completely disappear, leaving nothing behind. This leads to one of the most perplexing paradoxes in modern physics, the black hole information paradox. Imagine throwing a book into a black hole. The book contains information, the arrangement of letters, words, and sentences that make up its content. What happens to that information when the book falls into the black hole? According to general relativity, it is crushed into the singularity and lost forever. But this violates a fundamental principle of quantum mechanics, which states that information cannot be destroyed. Quantum mechanics is a deterministic theory, meaning that, in principle, you should always be able to reconstruct the past from the present. If information is lost in a black hole, then quantum mechanics breaks down. This is the information paradox, and it has baffled physicists for decades. How can we reconcile the seemingly contradictory predictions of general relativity and quantum mechanics? Is there a way to preserve information inside a black hole, or is our understanding of black holes fundamentally flawed? Several possible solutions to the information paradox have been proposed. One idea is that information is not actually destroyed, but is somehow encoded in the Hawking radiation. But how can the faint glow of Hawking radiation, which seems to be completely random, carry all the information that falls into a black hole? Another idea is that the information is stored on the surface of the black hole, on the event horizon itself. This is related to the holographic principle, which suggests that the information contained within a volume of space can be encoded on its boundary, like a hologram. Perhaps the most radical solution is that our understanding of black holes is incomplete, and that there is no singularity at the center of a black hole. Maybe quantum gravity effects prevent the formation of a singularity, replacing it with something else, such as a fuzzball or a firewall. These are exotic objects that would drastically alter our understanding of black holes. The information paradox is not just a theoretical puzzle. It has deep implications for our understanding of the fundamental laws of physics. Resolving the paradox could lead to a breakthrough in our quest for a theory of quantum gravity. Perhaps black holes are not the dead ends they appear to be, but rather they are portals to another universe, or perhaps just complex storage devices for the secrets of the cosmos. Imagine finding a way to decipher the Hawking radiation, like tuning a radio to the right frequency, revealing the history of everything that has ever fallen inside. What secrets might be unlocked? The possibilities are endless, and for scientists and dreamers alike, endless possibilities mean progress. As humanity continues to push the boundaries of scientific knowledge, who knows what marvels will be discovered at the edges of those dark gravitational prisons? But to even begin to ponder such complex topics, the scientific community needs to step back and consider a different way to view it all, and that may be closer than it seems. So, as humanity continues to push the boundaries of scientific knowledge, who knows what marvels will be discovered at the edges of those dark gravitational prisons? But to even begin to ponder such complex topics, the scientific community needs to step back and consider a different way to view it all. And that may be closer than it seems. Imagine, if you will, holding in your hands the ultimate instruction manual, the cheat sheet to the entire universe. This isn't just about understanding how a toaster works or even the life cycle of a star. We are talking about a single, elegant equation that explains everything, from the smallest subatomic particle to the largest supercluster of galaxies. A theory so complete, so profound, that it would forever alter our perception of reality. This is the holy grail of physics, the theory of everything. For centuries, scientists have striven to find a single framework that can explain all fundamental forces and particles in nature. It's a quest driven by the deeply held belief that the universe, in all its complexity, is ultimately governed by a few simple underlying principles. Think of it like a cosmic detective story where the clues are scattered across different fields of physics, and the goal is to piece them together to reveal the hidden truth. The first major breakthrough in this quest came in the 19th century, with the work of the Scottish physicist James Clerk Maxwell. Maxwell unified electricity and magnetism into a single force, electromagnetism. Before Maxwell, electricity and magnetism were seen as separate phenomena. But Maxwell showed that they were two sides of the same coin, mediated by a single force field. It was a monumental achievement, and it paved the way for future unifications. Imagine the impact of that discovery, a single equation that could describe everything from lightning strikes to the operation of a compass. In the 20th century, physicists made further progress with the development of the Standard Model of particle physics. The Standard Model is a comprehensive theory that describes the fundamental particles that make up matter and the forces that govern their interactions. It includes quarks, leptons, and bosons, and it explains three of the four known fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. The only force not included in the Standard Model is gravity. The Standard Model is an incredibly successful theory. It has been tested to astonishing precision, and it has accurately predicted the existence of new particles, such as the Higgs boson. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was a triumph for the Standard Model, confirming a key prediction of the theory. But despite its success, the Standard Model is not the final answer. It has several limitations. It doesn't explain the origin of mass, it doesn't account for dark matter and dark energy, and most importantly, it doesn't include gravity. This is where quantum gravity comes in. Quantum gravity is the missing piece of the puzzle, the final force that needs to be unified with the others. It is the theory that will reconcile general relativity with quantum mechanics, bridging the gap between the infinitely large and the infinitesimally small. Imagine if Maxwell had stopped at just electricity or just magnetism. The theory of everything is the new electromagnetism. But formulating a theory of quantum gravity is an incredibly challenging task. It requires us to grapple with some of the deepest mysteries of the universe. What is the nature of space and time? What happened at the Big Bang? What happens inside a black hole? These are questions that have puzzled physicists for decades, and answering them will require a radical shift in our understanding of reality. Some propose revolutionary ideas like string theory, vibrating filaments of energy that exist in 10 dimensions. Others suggest loop quantum gravity, quantizing space and time themselves into discrete units. The ambition of formulating a theory of everything is truly breathtaking. It's a quest to understand the ultimate laws of nature, to unlock the secrets of the cosmos, and to answer the fundamental questions that have plagued humanity for centuries. But the difficulty of this quest should not be underestimated. It will require the combined efforts of the brightest minds from around the world, pushing the boundaries of human knowledge to their absolute limits. Imagine the moment of discovery, the eureka moment when the final piece of the puzzle falls into place. What will the theory of everything look like? Will it be a single, elegant equation that fits on a T-shirt, or will it be a complex mathematical framework that requires supercomputers to solve? Will it confirm our current understanding of the universe, or will it reveal something completely unexpected? Perhaps you might ask, is this quest even possible? Is it arrogant to believe that we can understand the ultimate laws of nature? Maybe the universe is simply too complex, too chaotic to be fully understood. But even if we never achieve a complete theory of everything, the quest itself is invaluable. It drives us to explore the unknown, to push the boundaries of knowledge, and to inspire future generations of scientists. The journey is just as important as the destination. The search for a theory of everything is not just a scientific endeavor, it's a philosophical quest, a quest to understand our place in the universe. It's a testament to the human spirit, our insatiable curiosity, and our unwavering belief that we can unravel the mysteries of the cosmos. As we continue on this journey, we can be sure of one thing: the discoveries that await us will be nothing short of revolutionary. But with so many possible avenues to pursue, from extra dimensions to vibrating strings, how do scientists decide which path to follow? The answer may lie in probing the very fabric of space and time, venturing into realms beyond our everyday experience. But with so many possible avenues to pursue, from extra dimensions to vibrating strings, how do scientists decide which path to follow? The answer may lie in probing the very fabric of space and time, venturing into realms beyond our everyday experience. What if the universe's most fundamental building blocks aren't point-like particles, but something far more exotic, something akin to tiny, vibrating strings? This is the audacious premise of string theory, a revolutionary candidate for quantum gravity that has captivated physicists for decades. Imagine, if you will, taking a magnifying glass, not just to an atom, but far, far beyond. If you could zoom in close enough, string theory suggests that you would find that what we perceive as particles, like electrons and quarks, are actually minuscule one-dimensional strings, vibrating at different frequencies. Think of it like a guitar string. Pluck it one way, and you get one note. Pluck it another way, and you get a different note. Similarly, different vibrational modes of these fundamental strings correspond to different particles with different properties such as mass and charge. It is as if the entire universe is composed of an infinite symphony played out on these vibrating strings. But why strings? What problem does this seemingly outlandish idea solve? Well, string theory offers a potential solution to the problem of infinities that plague traditional attempts to reconcile general relativity and quantum mechanics. In conventional quantum field theory, particles are treated as point-like objects, leading to mathematical difficulties when calculating their interactions at extremely short distances. These calculations often result in infinite values, rendering the theory useless. String theory, on the other hand, avoids these infinities by smearing out the point-like particles into extended objects, the strings. This effectively softens the interactions at short distances, eliminating the troublesome infinities. It's like replacing a sharp knife with a blunt one. The blunt knife may not be as precise, but it also won't cut you. But perhaps the most compelling aspect of string theory is its ability to naturally incorporate gravity. One of the vibrational modes of the string corresponds to a massless particle with spin 2, precisely the properties expected of the graviton, the hypothetical quantum carrier of gravity. In other words, string theory predicts the existence of gravity, making it a natural candidate for a theory of quantum gravity. Is it all sounding too good to be true? There's a catch, of course. String theory comes with a rather hefty price tag, extra dimensions. In order for the theory to be mathematically consistent, it requires the existence of not just the 3 spatial dimensions that we experience, but a total of 10 dimensions. Where are these extra dimensions, you might ask? If they exist, why don't we see them? The prevailing idea is that these extra dimensions are curled up, incredibly small, and hidden from our view. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close you can see that it has a second dimension, the circumference of the hose. Similarly, the extra dimensions in string theory might be curled up at the Planck scale, far too small to be detected by our current experiments. These extra dimensions are not just mathematical curiosities. They are essential for the consistency of string theory. They also offer the tantalizing possibility of unifying all forces in nature. In string theory, the different forces and particles arise from the vibrations of the same fundamental strings, but in different dimensions. It's like saying that all the instruments in an orchestra are ultimately made of the same material, but they produce different sounds because of their different shapes and sizes. String theory is a mathematically elegant and conceptually appealing framework that offers a potential solution to the problem of quantum gravity. It predicts the existence of the graviton, the quantum carrier of gravity, and it offers the tantalizing possibility of unifying all forces in nature. However, it also requires the existence of extra, hidden spatial dimensions, a concept that is difficult to test experimentally. Is string theory the ultimate theory of everything, or is it just a beautiful mathematical dream? And what are the consequences if we could somehow prove these extra dimensions exist? So, is string theory the key? Is it the symphony of the universe played out on vibrating strings? Or is it a tantalizing mathematical mirage leading us down a blind alley? The jury is still out. But regardless of its ultimate fate, string theory has opened our minds to a truly mind-bending possibility: extra dimensions. What if the universe we see is just a small part of a much larger reality, a reality with dimensions beyond our everyday perception? Think about it for a moment. We live in a 3-dimensional world. We can move forward and backward, left and right, up and down. But what if there were other directions, other ways to move, that we simply cannot perceive? It sounds like science fiction, but the mathematics of string theory suggests that it is a very real possibility. These extra dimensions, if they exist, are not like the familiar 3 dimensions we experience. They are thought to be curled up, incredibly small, and hidden from our view. Imagine a tightrope walker. To an ant crawling along the rope, it's a one-dimensional world, a simple line. But to us, the tightrope has a second dimension, its thickness. The ant is simply too small to perceive it. Similarly, the extra dimensions in string theory might be curled up at the Planck scale, far too small for us to detect directly. It's like exploring a vast mansion and only being able to see 3 rooms, completely unaware of the dozens of other rooms hidden behind secret doors and passageways. What secrets could be hiding in those unseen chambers of the cosmos? But the idea of extra dimensions is not new. It actually dates back to the 1920s with the work of 2 physicists named Theodore Kaluza and Oscar Klein. Kaluza and Klein were attempting to unify gravity and electromagnetism into a single force. They realized that by adding a 4th spatial dimension to Einstein's theory of general relativity, they could derive Maxwell's equations for electromagnetism. It was a stunning result, suggesting that gravity and electromagnetism were simply different aspects of the same force,
unified in a higher dimensional space. Their theory, known as Kaluza-Klein theory, was a radical idea for its time. It was met with skepticism by many physicists, but it laid the groundwork for future explorations of extra dimensions. It's like discovering an old map hinting at a hidden treasure. You may not know exactly where it leads, but it sparks the imagination and inspires the search. Kaluza-Klein theory had its limitations. It couldn't explain all the known forces and particles in nature, and it suffered from mathematical inconsistencies. But it introduced the idea that extra dimensions could be more than just mathematical abstractions. They could have real physical consequences. In string theory, the idea of extra dimensions takes center stage. String theory requires 10 dimensions for mathematical consistency, and these extra dimensions are not just a minor detail. They are essential for the theory to work. Without them, string theory would be plagued by anomalies and inconsistencies. It's as if the extra dimensions are the scaffolding that holds the entire structure of string theory together. But what would it be like to live in a world with extra dimensions? Would we be able to perceive them directly? Probably not. The extra dimensions are thought to be curled up at the Planck scale, far too small for us to detect with our senses. But their presence could have subtle effects on the way gravity and other forces behave. Imagine, for example, that gravity could leak into the extra dimensions. This could explain why gravity is so much weaker than the other forces. Perhaps the gravitational force is diluted by spreading out into the extra dimensions, making it appear weaker in our three-dimensional world. Detecting these extra dimensions experimentally is a monumental challenge. The energies required to probe the Planck scale are far beyond anything we can currently achieve with particle accelerators. But there are other ways to look for evidence of extra dimensions. Perhaps we could detect them indirectly by searching for subtle deviations from the laws of gravity at short distances. Imagine building a miniature gravitational balance sensitive enough to measure the force of gravity between two tiny objects at very close range. If gravity behaves differently at short distances than predicted by general relativity, it could be a sign that gravity is leaking into extra dimensions. Another possibility is to look for evidence of Kaluza-Klein particles. In Kaluza-Klein theory, the extra dimensions are compact, meaning that they are curled up into circles. This leads to the prediction that there should be a whole tower of new particles, called Kaluza-Klein particles, with masses that are multiples of a fundamental mass scale. These particles would interact with ordinary matter, and they could potentially be detected at particle accelerators. The search for extra dimensions is a long shot, but the potential payoff is enormous. If we could discover extra dimensions, it would revolutionize our understanding of the universe and open up entirely new avenues of scientific exploration. It would be like discovering a new continent, filled with exotic landscapes and unknown creatures. The possibilities are endless. So, could it be that the universe we perceive is just a three-dimensional shadow of a higher dimensional reality? And if so, could we ever hope to detect these hidden realms? The quest continues, driving us to the very edge of human knowledge, where the familiar laws of physics begin to blur, and the true nature of reality remains tantalizingly out of reach. And if it turns out that we can detect other dimensions, what other realities could be discovered? But even if we could detect other dimensions, what other realities could be discovered? What if our universe, with all its stars, galaxies, and cosmic wonders, is not alone? What if it's just one of many, floating in a vast cosmic ocean? That's where the concept of brains comes in. Imagine a thin, flexible membrane, like a sheet of paper, floating in a higher dimensional space, a space called the bulk. This membrane, or brain, is a universe in its own right, a self-contained world with its own laws of physics. And what if our entire universe, everything we see and know, is just such a brain? It sounds like science fiction, but this is a serious proposal from string theory, a mind-bending idea that has profound implications for our understanding of the cosmos. Think of it like a cosmic slice of bread floating in a much larger loaf. We are confined to the surface of our bread slice, unaware of the other slices around us.
But what if we could somehow reach out and touch the other slices? What if we could interact with other universes? In brain cosmology, our universe is pictured as a three-dimensional brain embedded in a higher dimensional bulk. The bulk is a space with extra dimensions, dimensions that we cannot perceive directly. But these extra dimensions can have a profound effect on the way gravity and other forces behave on our brain. One of the most intriguing possibilities is that gravity can leak into the bulk. According to this scenario, the forces of electromagnetism, the weak nuclear force, and the strong nuclear force are confined to our brain. They are stuck to our three-dimensional world, unable to escape into the extra dimensions. But gravity is different. Gravity is the curvature of spacetime, and spacetime can exist in the bulk. So, gravity can spread out into the extra dimensions, diluting its strength on our brain. This could explain why gravity is so much weaker than the other forces. Perhaps gravity is not inherently weak, but it just appears weak to us because it is spread out over a much larger volume of space. It's like pouring a glass of water into a swimming pool. The water is still there, but it is so diluted that it is almost undetectable. The idea of gravity leaking into the bulk has some fascinating cosmological implications. It could affect the expansion rate of the universe, the formation of galaxies, and even the nature of dark energy, the mysterious force that is causing the universe to accelerate its expansion. It seems counterintuitive to suggest that something leaking out of our universe could be causing it to expand faster, doesn't it? Imagine two brains floating in the bulk, attracted to each other by gravity. As they get closer, the gravitational force between them increases, causing them to accelerate towards each other. Eventually, the two brains collide, releasing a huge amount of energy. This collision could be the Big Bang, the event that marked the beginning of our universe. In this scenario, our universe is not born from a singularity, but from a collision of two brains in a higher dimensional space. It's a radical idea, but it offers a potential solution to some of the problems with the standard Big Bang theory. The Big Bounce, as it has come to be known, could explain the universe's observed flatness and isotropy, but how could we ever test these brain world scenarios? The energies required to probe the bulk directly are far beyond anything we can currently achieve, but there are other ways to look for evidence of brains. Perhaps we could detect them indirectly by searching for subtle deviations from the laws of gravity on our brain. Imagine that scientists discovered that gravity was just a little bit stronger or weaker in one particular part of the universe than in other parts. This would be pretty crazy and require a whole new set of models to explain. Another possibility is that we could detect gravitational waves that have traveled through the bulk. These gravitational waves would carry information about the geometry of the bulk, providing us with a glimpse into the hidden dimensions. It would be like sending a sonar signal into a dark cave, mapping out the shape of the cave by analyzing the echoes. Brains and the bulk. Cosmic membranes floating in a higher dimensional space. It's a concept that challenges our deepest assumptions about the nature of reality. Are we alone in the universe? Or are there other universes, other brains, floating alongside us, just beyond our perception? And how does space-time itself, so mysterious, fit into all of this? The questions abound, and each answer seems to beget even more questions than before. It may require humanity to question everything it thinks it knows about the universe to discover these answers. Maybe someday in the not-so-distant future we may know for sure, but for now. So, brains might be the cosmic stage upon which our universe plays out its existence. But what if we zoom in again, past the brains, past even the strings themselves? What if we find that space and time, the very fabric of reality, are not smooth and continuous, but rather woven from something far more fundamental? Enter loop quantum gravity, or LQG, a major alternative approach to quantizing gravity. Forget strings vibrating in 10 dimensions. Loop quantum gravity takes a radically different approach. Instead of starting with particles and forces, LQG focuses on quantizing space-time geometry itself. Think of it like this.
String theory attempts to unify the forces of nature first and foremost, with gravity emerging as a consequence. Loop quantum gravity, on the other hand, says that we must first understand the quantum nature of space and time, and then gravity will naturally fall out. Imagine looking at a woven tapestry. From afar, it appears to be a smooth, continuous surface, but up close you can see that it is made of individual threads, interlocked and interwoven to create the overall pattern. Loop quantum gravity suggests that space-time is similar. At the smallest scales, it is not a smooth continuum, but rather a network of interconnected loops, forming discrete atoms of space and volume. These aren't atoms in the traditional sense of matter, but rather fundamental units of space itself. These loops are not just mathematical abstractions. They are physical entities carrying information about the quantum state of the gravitational field. They are interconnected in a network called a spin network, a kind of quantum web that weaves the fabric of space-time. It's as though the universe is one giant, ever-evolving spiderweb made of pure geometry. The implications of this are profound. If space is quantized, it means that there is a smallest possible unit of volume, a smallest possible length. There is no such thing as infinitely small. Space comes in discrete chunks, like tiny building blocks. The same is true for time. There is a smallest possible unit of time, a shortest possible duration. Time does not flow smoothly and continuously, but rather in discrete steps like frames in a movie. Think of it like a digital photograph. From afar, it looks like a smooth, continuous image, but up close you can see that it is made up of individual pixels, tiny squares of color. Loop quantum gravity eliminates the singularities, the points of infinite density that plague general relativity. Because space and time are quantized, there is a maximum density and a minimum volume. You can't squeeze matter into an infinitely small point. Eventually you reach the Planck scale, where the quantum nature of space-time prevents further compression. It is almost as though the universe has a built-in safety mechanism to prevent it from collapsing into infinitely small points. One of the key features of loop quantum gravity is something called background independence. What does this mean? In many theories of physics, including general relativity and string theory, space-time is treated as a fixed background, a stage upon which events unfold. But loop quantum gravity takes a more radical approach. In LQG, space-time itself is dynamic and evolving. It is not a fixed background, but rather a quantum field that evolves according to its own laws. It is as though the stage itself is part of the play, changing and evolving along with the actors. This background independence is a major departure from traditional physics, and it has some profound consequences. It means that there is no need to assume a pre-existing space-time in order to formulate a theory of quantum gravity. Instead, space-time emerges from the underlying quantum structure of the spin networks. Now you might be asking, how does loop quantum gravity compare to string theory? Both are attempts to quantize gravity, but they take very different approaches. String theory starts with particles and forces and attempts to unify them in a higher dimensional space. Loop quantum gravity starts with space-time geometry and attempts to quantize it directly. String theory is often described as a top-down approach, starting with a grand, overarching theory and working down to the details. Loop quantum gravity is often described as a bottom-up approach, starting with the fundamental building blocks of space and time and working up to the larger structures. They are almost opposite in terms of their approach to the problem. Which approach is correct? No one knows for sure. Both string theory and loop quantum gravity are still works in progress. They both have their strengths and weaknesses, and they both face significant challenges. But they both offer tantalizing glimpses into the quantum nature of gravity, and they both inspire us to push the boundaries of human knowledge. Could it be that space, as we perceive it, is nothing more than an illusion, a large-scale approximation of something far stranger and more granular at the quantum level? Perhaps time itself does not flow in a continuous manner, but rather in discrete steps, like the ticking of a cosmic clock. And can scientists somehow craft experiments that are capable of reaching these new scales and testing these new theories? The answers to these questions may lie within the intricate and complex structures of what are known as spin networks, which are a cornerstone of loop quantum gravity. Could it be that space, as we perceive it, is nothing more than an illusion, a large-scale approximation of something far stranger and more granular at the quantum level? Perhaps time itself does not flow in a continuous manner, but rather in discrete steps, like the ticking of a cosmic clock. And can scientists somehow craft experiments that are capable of reaching these new scales and testing these new theories? The answers to these questions may lie within the intricate and complex structures of what are known as spin networks, which are a cornerstone of loop quantum gravity. Think of the very fabric of space itself, not as a smooth, continuous canvas upon which the drama of the universe unfolds, but as something woven, knitted together from countless threads, each thread representing a quantum state of gravity. These threads, these lines of force, are the fundamental building blocks of space itself, and when they intertwine and connect, they form a network, a sprawling, ever-shifting structure known as a spin network. Imagine a vast, three-dimensional spider web, spun not from silk, but from pure geometry. At each intersection, each node in this web, lies a quantum of space, an indivisible unit of volume. These quanta are incredibly small, far smaller than even an atom existing at the Planck scale. But it is from these tiny building blocks that the familiar space we experience emerges. It's like a pointillist painting by Georges Seurat. From a distance you see a coherent image, a landscape, a portrait. But up close, you realize it is made up of countless tiny dots of color. Similarly, the smooth, continuous space of Einstein's general relativity emerges as an approximation, a large-scale average, from the underlying quantum geometry of the spin network. But what does this all mean? What are these spin networks actually telling us? Well, each link, each connection in the network, represents a quantum of area. It's as if space itself is divided into tiny facets, each with a specific quantized area. And each node, each intersection, represents a quantum of volume, an indivisible unit of space. The values assigned to these links and nodes are not arbitrary. They are determined by the laws of quantum mechanics. The entire network is a representation of the quantum state of the gravitational field, a snapshot of gravity at the smallest possible scale. And here's where it gets really interesting. These spin networks are not static. They are constantly evolving, morphing, and changing. Links can break and reconnect, nodes can appear and disappear. It's like a living, breathing network constantly adapting to the ever-changing quantum landscape. This dynamic nature of the spin networks reflects the fact that spacetime itself is not fixed and immutable, but rather a dynamic entity, evolving according to the laws of quantum gravity. This idea of quantized space also has a profound consequence. It eliminates the infinities that plague other theories of quantum gravity. Because there is a smallest possible unit of volume, you cannot squeeze matter into an infinitely small point. The density is limited and the singularities predicted by general relativity simply disappear. It's like the universe has a built-in safety valve preventing it from collapsing into infinitely small points. This is one of the key triumphs of loop quantum gravity, its ability to tame the infinities and provide a consistent description of gravity at the Planck scale. Picture a black hole, not as a point of infinite density, but as a highly complex, densely packed spin network. The event horizon, the point of no return, is not a sharp boundary, but rather a fuzzy quantum region, where the spin network is stretched and distorted to its limits. What happens to matter that falls into this quantum black hole? Does it disappear into a singularity? Or does it become part of the spin network, contributing to its complexity and its evolution? The answer to this question may hold the key to resolving the black hole information paradox. The beauty of spin networks lies in their simplicity and their elegance.
They are a minimal, background-independent description of quantum geometry, requiring no extra dimensions or hypothetical particles. It is a universe built from the most fundamental ingredients, space and time themselves. But how can we visualize these spin networks? How can we make sense of these abstract mathematical structures? Are they simply theoretical constructs, or do they have a real physical existence? Perhaps, in the future, with advanced quantum computers, we will be able to simulate these spin networks to visualize their dynamic evolution and to explore their properties in detail. Imagine watching a movie of the quantum fabric of space-time, seeing the spin networks morph and change, responding to the flow of energy and matter. What patterns would we see? What new insights would we gain into the nature of gravity? While we may not be able to see these spin networks directly, we can look for indirect evidence of their existence. Perhaps the cosmic microwave background, the afterglow of the Big Bang, contains subtle patterns that reflect the quantum geometry of the early universe. Or perhaps the behavior of black holes or the properties of gravitational waves could reveal the telltale signs of quantized space. The quest to understand spin networks is not just about understanding the quantum nature of gravity. It's about understanding the fundamental nature of reality itself. It's about grappling with the deepest questions about space, time, and the universe. Are we on the verge of a paradigm shift in our understanding of the cosmos, a revolution as profound as the one initiated by Einstein himself? If space is truly woven from these quantum threads, what are the looms that create this cosmic tapestry, and what untold wonders might lie beyond our current comprehension? Perhaps peering into the structure of spin networks is more than just answering theoretical questions, and is also about to stumble upon something new. So, if space is truly woven from these quantum threads, what are the looms that create this cosmic tapestry, and what untold wonders might lie beyond our current comprehension? Perhaps peering into the structure of spin networks is more than just answering theoretical questions, and is also about to stumble upon something new. But if you thought that the quantum realm was strange, already prepare yourself for something even more bizarre. Imagine the smoothest surface you can possibly conceive, perhaps the surface of a perfectly still lake on a windless day, or the face of a meticulously polished mirror. Now, zoom in. Not with an ordinary microscope, but with a device capable of resolving distances at the Planck scale. What would you see? Would you find the smooth, continuous surface you imagined? The answer, according to quantum gravity, is a resounding no. Instead, you would encounter something far more turbulent, far more chaotic: quantum foam. Quantum foam is the mind-bending idea that space-time, at the smallest scales, is not smooth and placid, as Einstein envisioned, but rather a roiling sea of quantum fluctuations, a frothing ocean of virtual particles and microscopic wormholes constantly popping in and out of existence. It's like the head on a freshly poured beer, constantly forming and reforming, a dynamic and unpredictable froth. But what causes this quantum foam? The answer lies in the uncertainty principle, that cornerstone of quantum mechanics we have previously discussed. The uncertainty principle tells us that we can never know both the position and the momentum of a particle with perfect accuracy. The more precisely we know one, the less precisely we can know the other. This principle also applies to energy and time. The more precisely we know the energy of a system, the less precisely we can know the time over which that energy is measured, and vice versa. This means that even in empty space, there is always a tiny amount of uncertainty in the energy. This uncertainty allows for the spontaneous creation of virtual particles, particles that pop into existence for a fleeting moment, only to disappear again almost immediately. These virtual particles are not just mathematical abstractions, they have real physical effects. They contribute to the energy density of space, they affect the interactions between particles, and they even warp space-time itself. Now imagine these virtual particles appearing and disappearing at the Planck scale, creating tiny ripples and fluctuations in the fabric of space-time.
Imagine microscopic wormholes, tunnels through spacetime, spontaneously forming and collapsing, connecting distant regions of the universe through quantum shortcuts. It's a mind-boggling picture, a universe far more dynamic and unpredictable than anything Einstein could have imagined. Einstein's vision was so clean, so organized. What would he have thought about this? Both string theory and loop quantum gravity predict variations of this quantum foam, though their descriptions differ in detail. In string theory, the quantum foam arises from the vibrations of strings at the Planck scale, creating a kind of fuzzy, extended spacetime. In loop quantum gravity, the quantum foam arises from the fluctuating geometry of the spin networks, creating a granular, discrete spacetime. But regardless of these details, both theories agree on one thing. At the Planck scale, spacetime is not smooth and continuous, but rather a dynamic and uncertain quantum foam. It is a place where the familiar laws of physics break down, where cause and effect blur, and where the true nature of reality remains hidden, waiting to be unveiled. So what does this quantum foam mean for our understanding of the universe? Does it mean that Einstein was wrong? Not necessarily. Einstein's general relativity is still an incredibly accurate description of gravity at large scales. But at the Planck scale, the quantum effects become dominant, and Einstein's smooth, placid spacetime gives way to the turbulent depths of the quantum foam. It's like looking at a painting by Vincent van Gogh. From a distance, it looks like a coherent scene, a landscape, a portrait. But up close, you see the swirling brush strokes, the impasto texture, the chaotic energy of the artist's hand. Similarly, Einstein's general relativity is a smooth, large-scale approximation of the underlying quantum reality, a reality that is far more complex and far more bizarre. The quantum foam is not just a theoretical curiosity. It may have real physical consequences. It could affect the way light propagates through space, causing it to be slightly fuzzy or blurred. It could affect the behavior of black holes, altering their evaporation rate and their information content. And it could even affect the expansion rate of the universe, contributing to the mysterious dark energy that is causing the universe to accelerate its expansion. But how can we ever hope to study the quantum foam directly? The Planck scale is so small, the energies involved are so high that it seems impossible to probe this realm with our current technology. Perhaps we can look for indirect evidence, searching for subtle effects in the cosmic microwave background, or in the behavior of black holes, or in the properties of gravitational waves. Imagine building a telescope so powerful that it could resolve the quantum fluctuations of space-time, seeing the virtual particles popping in and out of existence, watching the microscopic wormholes forming and collapsing. What a sight that would be, a glimpse into the very fabric of reality. While that technology may be a distant dream and seems impossible right now, maybe future quantum technologies can take on this task. The search for the quantum foam is a quest to understand the ultimate nature of reality, a quest that may require us to abandon our most cherished assumptions about space, time, and the universe. Are we prepared to dive into these turbulent depths, to confront the unknown, and to embrace a reality that is far stranger and more wonderful than we ever thought possible? Are we ready for what we may discover? What if reality, as we perceive it, is not actually reality at all, but just a projection? So, are we ready for what we may discover? What if reality, as we perceive it, is not actually reality at all, but just a projection? Imagine walking into a darkened movie theater. On the screen, a thrilling chase scene unfolds, filled with breathtaking landscapes and heart-pounding action. You are completely immersed in this three-dimensional world, experiencing every twist and turn as if you were right there. But what if I told you that the entire movie, the characters, the scenery, the action, everything, is actually encoded on a flat, two-dimensional film? This, in essence, is the mind-bending idea behind the holographic principle, the suggestion that all the information contained within a volume of space can be represented on its boundary surface, like a hologram. Think of it like a cosmic hard drive, where the entire universe is stored on a surface that surrounds it. It sounds like something straight out of a science fiction movie, doesn't it? but this is a serious proposal, born from the depths of theoretical physics, a concept that challenges our deepest assumptions about the nature of reality. The holographic principle didn't just spring out of thin air. It has its roots in the study of black hole thermodynamics, the bizarre laws that govern the behavior of black holes. Back in the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a remarkable discovery. They found that black holes, despite being the ultimate destroyers, actually possess a kind of entropy, a measure of disorder. This entropy is proportional to the surface area of the black hole's event horizon, the point of no return beyond which nothing can escape. This was a shocking result. It suggested that all the information about what fell into the black hole is somehow encoded on its surface, on the event horizon. It was as if the black hole was a cosmic library, storing all its secrets on its surface, not in its interior. Now fast forward to the 1990s, when physicist Juan Maldacena made a groundbreaking discovery that provided concrete realization to holographic ideas. Maldacena discovered a specific example of the holographic principle in string theory, a correspondence between a theory of gravity in a five-dimensional space called anti-de Sitter space and a quantum field theory living on the four-dimensional boundary of that space. This correspondence, known as the ADS-CFT correspondence, is a mathematical Rosetta Stone, allowing physicists to translate between the language of gravity and the language of quantum field theory. It's as if we have found a secret code that allows us to decipher the mysteries of the universe. The ADS-CFT correspondence is not just a theoretical curiosity. It has become a powerful tool for studying strongly interacting quantum systems, such as the quark-gluon plasma, a state of matter that existed in the very early universe. This connection between gravity and quantum field theory suggests that our three-dimensional reality could be merely a projection from a lower dimensional surface, a kind of cosmic hologram. It's a mind-blowing thought, isn't it? That everything we see and experience, the stars, the galaxies, the people, the planets, even you yourself, are just projections from a distant surface. It would be akin to discovering that the world is not as tangible as previously assumed. Could this lead to us understanding that what we call reality is not that tangible after all? That the chair that you are sitting on, the floor beneath your feet, the very air you breathe, are all illusions, generated from information encoded on a distant boundary. It's a concept that challenges our deepest intuitions about reality, existence, and observability. Imagine that the surface of the sun is a giant movie screen, and all the events on Earth are simply projected onto this screen from some distant source. What would that mean for our understanding of cause and effect? Would it mean that we are not truly free agents, but rather puppets dancing to the tune of some unseen puppeteer? What new realities would we see? So, are we ready for what we may discover? What if reality, as we perceive it, is not actually reality at all, but just a projection? What if the theater we call the universe has an usher, a messenger, constantly flitting about, delivering the cosmic mail? What if this messenger is the key to finally understanding gravity at the quantum level? Enter the graviton, the hypothetical particle believed to mediate the force of gravity. Imagine every force in nature as a game of catch. When you throw a ball to another person, you are exerting force on that ball. The electromagnetic force has photons, the strong nuclear force has gluons, and so on. For gravity, that ball would be the graviton. If gravity operates at a quantum level, there needs to be a quantum particle responsible for carrying gravity. Now, if the holographic principle holds true, and our universe is indeed a projection from some distant surface, could the graviton be the projector, the beam of light that creates our reality? This hypothetical particle, the graviton, is the quantum messenger of gravity. If gravity operates at a quantum level, there needs to be a quantum particle responsible for carrying gravity. It is an essential cornerstone of most quantum gravity theories, but as of right now, it's entirely theoretical. So what exactly do we know, or rather, what do we predict about this elusive particle? For starters, the graviton is expected to be massless. Unlike the bosons mediating the weak and strong nuclear forces which have mass, the graviton, like the photon, needs to be without mass, so that gravity has an infinite range. The graviton also needs to have a spin of 2, which is derived from quantizing Einstein's equations, those complex mathematical formulations that describe the curvature of spacetime. This spin determines how the particle interacts with other particles, and a spin of 2 is necessary to produce the attractive force we experience as gravity. It needs to be attractive because gravity is only known as an attractive force and not repulsive. This sets it apart from other known forces in nature. But here's the rub. Despite being a cornerstone of many quantum gravity theories, the graviton remains stubbornly elusive. The problem is that gravity is by far the weakest of the 4 fundamental forces. To get a sense of just how weak, consider this. A simple refrigerator magnet can overcome the entire gravitational pull of the Earth to lift a paperclip. Think about that. The entire mass of our planet pulling downwards is easily defeated by a tiny magnet. This extreme weakness makes detecting individual gravitons incredibly difficult, perhaps even impossible with current technology. The force of gravity is so weak that its messenger, the graviton, is incredibly hard to detect, as it interacts very weakly with matter, making it extremely difficult to isolate and measure. Imagine trying to hear a whisper in the middle of a rock concert. The gravitational force between 2 ordinary objects is so minuscule that the number of gravitons exchanged is virtually undetectable. To detect a single graviton, you would need an incredibly massive and sensitive detector, something far beyond our current capabilities. It is as if we are trying to weigh an atom with a scale designed to measure elephants. Detecting gravitational waves, those ripples in space-time predicted by Einstein, is already a monumental achievement, requiring incredibly sensitive instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory. But detecting individual gravitons is a whole different ballgame, a leap in sensitivity of many orders of magnitude. Gravitational waves are detectable due to the sheer magnitude of the events that create them, like supermassive black holes colliding at millions of miles per hour. Imagine trying to detect one by just looking at the 2 billiard balls colliding. So, if direct detection of gravitons is seemingly impossible, does that mean we should give up the search? Absolutely not. The quest to find the graviton is not just about confirming its existence. It's about testing our fundamental understanding of gravity and the quantum world. Even though detection is nearly impossible, it does not mean that it is not worth it. Perhaps we can find indirect evidence of the graviton, subtle effects that reveal its presence without directly detecting it. Perhaps by studying the cosmic microwave background, the afterglow of the Big Bang, we can find patterns that reveal the quantum nature of gravity and the role of the graviton in the early universe. Perhaps, by probing the mysteries of black holes, we can uncover clues about how gravity behaves at the quantum level. Maybe, just maybe, someday in the future, our telescopes will be strong enough, the graviton, the messenger of gravity. A hypothetical particle that may hold the key to unifying Einstein's elegant universe with the bizarre world of quantum mechanics. Its existence is a cornerstone prediction for quantum gravity theories, but its detection remains one of the greatest challenges in modern physics. However, its significance far outweighs the trouble in confirming it, and perhaps a deeper dive into high-precision experiments might shed some light on the subject. So, the graviton, elusive as it may be, acts as a beacon, guiding us toward the horizon of quantum gravity. Yet, the question lingers. How do we actually test these grand, sweeping theories when the very energies required are so far beyond our reach?
Are we forever confined to the realm of theoretical speculation, or can we devise ingenious experiments capable of glimpsing Planck-scale physics? That is 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Our most powerful particle accelerators, like the Large Hadron Collider near Geneva, Switzerland, slam particles together at energies equivalent to a mosquito hitting a freight train. It is an amazing feat of human engineering and a testament to our ingenuity and ability to understand the universe. These collisions allow us to probe the subatomic world, to create new particles, and to test the predictions of the Standard Model. But even these incredible machines fall far short of the energies needed to directly probe the Planck scale, where quantum gravity is expected to reign supreme. To reach Planck scale energies, we would need a particle accelerator the size of our galaxy, an instrument so gargantuan that it strains the very limits of imagination. Short of harnessing the energy of a collapsing star, direct experimental probes remain firmly out of reach. So, are we simply out of luck? Is the quest for quantum gravity doomed to remain a purely theoretical endeavor? Fortunately, the answer is no. While direct probes may be impossible, physicists are not easily deterred. They are masters of ingenuity, skilled at devising clever, indirect tests that can reveal the subtle effects of quantum gravity without requiring us to reach those extreme energy scales. It is like trying to understand the workings of a car engine without actually taking it apart. You can listen to the sound of the engine, measure its performance, and analyze its exhaust fumes to gain insights into its inner workings. The key is to search for subtle, indirect effects that might betray the presence of quantum gravity. These effects might be hidden in the cosmic microwave background, the afterglow of the Big Bang, or in the behavior of black holes, or even in the very fabric of spacetime itself. The hunt is on, and the stakes are high. What is at risk if we do not find the theory of quantum gravity? That would mean that we may need to adjust some of our current laws that govern how we understand the universe. One promising avenue is to search for subtle deviations from the predictions of general relativity. General relativity is an incredibly accurate theory, but it is not perfect. It has some known limitations, and it is possible that quantum gravity effects could cause slight deviations from its predictions. Imagine, for example, performing extremely precise measurements of the orbits of planets in our solar system. If quantum gravity causes subtle changes in the gravitational field, it could lead to tiny but measurable deviations from the orbits predicted by general relativity. It would be like discovering a slight imperfection in a perfectly round ball. Another approach is to search for violations of fundamental symmetries. Symmetries are fundamental principles that govern the laws of physics. For example, the laws of physics are believed to be the same regardless of where you are in the universe, a principle known as translational symmetry. They should be the same no matter how you are moving, a principle known as Lorentz symmetry. If quantum gravity breaks these symmetries, it could lead to observable effects. It is much like finding a crack in a mirror. This crack would cause the reflection to be distorted. These effects might be incredibly small, but with sufficiently precise instruments, they could be detectable. Physicists have been exploring various tests, including extremely high-precision experiments. Perhaps the answer lies not in probing the cosmos, but in the laboratory, with tabletop experiments of unprecedented sensitivity. What if, within the confines of a carefully controlled environment, we could coax nature to reveal its quantum gravitational secrets? It may seem impossible, but in the realm of quantum physics, with some ingenuity, it may be possible. Perhaps the most astonishing laboratory in the universe isn't buried deep beneath the Swiss Alps or orbiting high above the Earth, but the cosmos itself. The universe, in its vastness and its violent beauty, provides the ultimate testing ground for our theories, a canvas upon which the drama of quantum gravity may be written. But what specific cosmic clues are we looking for? And where do we even begin to search? One of the most promising avenues for exploration lies in the cosmic microwave background, the faint afterglow of the Big Bang. Imagine holding a photograph of the universe as a newborn, only 380,000 years after its birth. This afterglow, this ancient light, is not perfectly uniform. It has tiny temperature fluctuations, minuscule variations that represent the seeds of all the structures we see today, galaxies, clusters of galaxies, and the vast cosmic web. These fluctuations are like fingerprints, subtle clues about the conditions that prevailed in the very early universe, a time when gravity and quantum mechanics were inextricably intertwined. Perhaps within these subtle temperature variations, we might find the imprints of quantum gravity, subtle patterns that could confirm or refute our current theories. Now, consider something far more dramatic, something far more energetic: gamma-ray bursts. These are the most powerful explosions in the universe, fleeting bursts of high-energy radiation that can outshine entire galaxies. Scientists are not yet sure what causes these cataclysmic events, but some theories suggest they are linked to the collapse of massive stars or the merger of neutron stars. Could these gamma-ray bursts carry information from the quantum gravity era? Could they be messengers from the universe's most extreme environments, where gravity and quantum mechanics collide? Imagine that these explosions, when first formed, were not constrained by spacetime like our current observations are. With this possibility, they could have been infinitely big as the universe, then collapsed on themselves. Think about it like this. If spacetime itself were a woven fabric, a quantum gravity event, such as that would be big enough to tear it. Now it collapses, becoming the gamma-ray burst we are observing through instruments to this day. That initial tear would provide us clues. As those gamma rays travel across billions of light years, they might interact with the quantum foam of space-time, the roiling sea of quantum fluctuations that we discussed earlier. These interactions could leave subtle imprints on the gamma rays, altering their polarization or their energy spectrum. By studying these subtle changes, scientists hope to learn about the nature of quantum gravity and the structure of space-time at the Planck scale. It is as if we are using the gamma rays as cosmic probes, sending them out into the universe to explore the unknown. One of the key challenges is to distinguish these quantum gravity effects from other phenomena that could alter the gamma rays as they travel through space. The universe is filled with gas, dust, and magnetic fields, all of which can interact with the gamma rays and change their properties. It's like trying to hear a faint whisper in a crowded room. To overcome this challenge, scientists are using multiple telescopes, both on the ground and in space, to observe gamma-ray bursts across the electromagnetic spectrum. By combining these observations, they can disentangle the various effects and isolate the subtle signatures of quantum gravity. The universe, in its vastness and its complexity, acts as a laboratory for fundamental physics. It provides us with a unique opportunity to test our theories and to explore the unknown. From the faint afterglow of the Big Bang to the violent explosions of gamma-ray bursts, the cosmos is filled with clues waiting to be deciphered. It is a grand cosmic puzzle, and the search for quantum gravity is one of the most exciting chapters in that story. But is it possible that the answers we seek are not written in light, but in the very fabric of space-time itself? What are those new gravitational waves trying to tell us? So the cosmos is essentially shouting secrets at us all the time using gamma rays, the cosmic microwave background, a whole lot of other ways. It is up to us to construct the instruments to hear them, to use the entire universe as one giant physics lab to explore gravity at the quantum level. But is it possible that the answers we seek are not written in light, but in the very fabric of space-time itself? What if the universe has been singing this entire time and humanity just created the ears to hear the song? Imagine tossing a pebble into a still pond. Ripples spread outward, disturbing the placid surface. Now,
Envision that pond as the fabric of space-time, and instead of a pebble, picture cataclysmic cosmic events, colliding black holes, the explosive death throes of supermassive stars, or even the very birth of the universe itself. These events create ripples, not in water but in space-time itself, gravitational waves. Predicted by Albert Einstein over 100 years ago, these waves are not merely theoretical curiosities, but a fundamental aspect of general relativity. It is almost like they are proof of it. They are distortions in the very geometry of space and time, propagating outward at the speed of light, carrying with them information about the events that created them. For decades, they remained elusive, a whisper on the edge of detection. It was almost like scientists were looking into the past. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by directly detecting gravitational waves for the first time. It was a monumental achievement, a confirmation of Einstein's prediction and a brand new window into the universe. The universe has been singing to us for billions of years using light. Now we can hear it in song. The first detection came from the merger of two black holes, over 1 billion light-years away. Scientists heard the chirp, a faint but unmistakable signal that confirmed the existence of gravitational waves and opened up a new era of astronomical observation. But what if these gravitational waves are not just messengers of cosmic events, but also potential messengers from the very early universe carrying imprints of quantum gravity physics? What if they are a kind of time capsule? According to the theory of cosmic inflation, the universe underwent a period of incredibly rapid expansion in the first tiny fraction of a second after the Big Bang. This inflation, driven by unknown physics, would have generated primordial gravitational waves, ripples in space-time that could carry information about the quantum gravity era. That is information from 13.8 billion years ago. These primordial gravitational waves are different from the gravitational waves produced by colliding black holes. They are not created by specific events, but are instead a kind of background hum, a cosmic symphony generated by the expansion of the universe itself. Detecting these primordial gravitational waves would provide direct evidence for inflation, and would give us a glimpse into the quantum gravity physics that governed the very first moments of the universe. What did those first moments sound like? Was it a whisper or an incredible explosion? But detecting these primordial gravitational waves is an incredibly challenging task. The signals are extremely faint, much fainter than the gravitational waves detected by LIGO. They are also mixed with other gravitational waves from astrophysical sources, such as colliding black holes and neutron stars. It's like trying to pick out a single instrument in a vast orchestra. One of the key challenges is distinguishing these ancient signals from the astrophysical sources. To do this, scientists need to create very sensitive instruments that can measure the polarization of gravitational waves. Polarization is the direction in which a wave oscillates, and primordial gravitational waves are expected to have a unique polarization pattern known as B modes. That unique pattern is almost like a fingerprint of time. Detecting these B modes would be a smoking gun, providing strong evidence for inflation and the existence of primordial gravitational waves. But B modes can also be generated by other sources, such as dust in our galaxy. It's like trying to find a specific fingerprint on a dusty surface. To overcome this challenge, scientists are building new gravitational wave detectors, both on the ground and in space. These detectors are designed to be incredibly sensitive to B modes and to minimize the contamination from other sources. Think about it. These researchers are trying to catch echoes from nearly 14 billion years ago. One promising project is the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector that will consist of 3 spacecraft, separated by millions of kilometers, flying in formation around the Sun. LISA will be able to detect gravitational waves at much lower frequencies than LIGO, opening up a new window into the universe and allowing us to search for primordial gravitational waves. It is like building a giant ear in space, capable of hearing the faintest whispers from the early universe. Detecting primordial gravitational waves would be a monumental achievement, a triumph of human ingenuity, and a testament to our unwavering desire to understand the universe. It would provide us with a direct glimpse into the quantum gravity era and would revolutionize our understanding of the cosmos. Imagine if we could use all the scientific progress humanity has made to finally hear the birth cry of the universe. These future detectors are not just tools for scientific discovery. They are gateways to a deeper understanding of the universe and the fundamental laws that govern it. They have the potential to unlock some of the greatest mysteries of science, providing us with a glimpse into the quantum gravity era and revolutionizing our understanding of the cosmos. What other doors would open? So future detectors are not just tools for scientific discovery. They are gateways to a deeper understanding of the universe and the fundamental laws that govern it. They have the potential to unlock some of the greatest mysteries of science, providing us with a glimpse into the quantum gravity era and revolutionizing our understanding of the cosmos. What other doors would open? But what if the key to unlocking the secrets of quantum gravity isn't hidden in the farthest reaches of the cosmos, but is waiting to be discovered much closer to home, maybe even within the confines of a humble laboratory? Is it truly possible to glimpse the subtle whispers of quantum gravity without the need for colossal particle accelerators or telescopes that span the solar system? Can we, through sheer ingenuity and meticulous experimentation, coax nature to reveal its deepest secrets on a tabletop? The challenge is immense, no doubt. We are talking about probing the Planck scale, that realm of unimaginable smallness where space and time themselves become fuzzy and uncertain. The energies required to directly probe this realm are far beyond anything we can currently achieve. But what if, instead of trying to brute force our way to the Planck scale, we could find a more subtle approach, a way to amplify the faint effects of quantum gravity to a level that is detectable in the laboratory? It is akin to listening for the faint rustling of leaves during a hurricane. Near impossible, but could we use the storm itself to amplify those sounds? One promising avenue lies in exploiting the bizarre and counterintuitive world of quantum entanglement. Remember those entangled particles, linked in such a way that they share the same fate, no matter how far apart they are? What if we could use this spooky action at a distance to amplify the effects of quantum gravity? Imagine creating two entangled particles and placing them in separate, highly sensitive detectors. If quantum gravity causes subtle fluctuations in space-time, these fluctuations might affect the entanglement between the particles. By carefully measuring the entanglement, we might be able to detect these tiny effects, even if they are far below the threshold of our current instruments. It's like using the entanglement as a magnifying glass, amplifying the faint signals of quantum gravity to a detectable level. Another approach involves high-precision laser measurements. Lasers are among the most precise instruments ever created. They can measure distances with incredible accuracy down to the level of atoms. What if we could use lasers to measure the distance between two objects and looked at fluctuations in that distance in a way that might reveal the quantum structure of space? Imagine setting up two mirrors, separated by a carefully controlled distance. If quantum gravity causes space-time to be grainy and fluctuating, it could lead to tiny variations in the distance between the mirrors. By shining a laser beam between the mirrors and measuring the interference pattern, we might be able to detect these subtle variations. It's like using a laser as a cosmic ruler, measuring the fine structure of space-time with unprecedented precision. Yet another possibility lies in testing fundamental symmetries at low energies. Symmetries, as we discussed before, are fundamental principles that govern the laws of physics. But what if quantum gravity breaks these symmetries ever so slightly? Could we detect these violations by performing incredibly sensitive experiments at low energies? Imagine testing the symmetry between matter and antimatter, a symmetry known as charge parity time reversal symmetry. If quantum gravity violates this symmetry, it could lead to tiny differences in the properties of matter and antimatter. By carefully comparing the properties of matter and antimatter, we might be able to detect these subtle violations. It's like searching for a tiny crack in a seemingly perfect mirror, a crack that reveals a deeper, more complex reality. Now, it's important to acknowledge the speculative nature of these approaches. These experiments are incredibly challenging, pushing the limits of our current technology, and there is no guarantee that they will reveal anything. But the potential reward is enormous. If we could detect the subtle effects of quantum gravity in the laboratory, it would revolutionize our understanding of the universe. It would be a triumph of human ingenuity and a testament to our unwavering curiosity. Perhaps the answers to the universe's greatest mysteries are not hidden in the echoes of the Big Bang or the hearts of black holes, but in the subtle dance of particles, in the precise measurements of lasers, and the careful testing of symmetries. Perhaps the key to understanding the cosmos lies not in escaping our home, but in appreciating the clues it has left behind. With the right ingenuity and a keen eye for the subtle, those answers might just be a few carefully crafted experiments away. Where does all the information that enters a black hole go? So, with the right ingenuity and a keen eye for the subtle, those answers might just be a few carefully crafted experiments away. But what happens when we turn our gaze back to those cosmic behemoths, those inescapable gravitational wells known as black holes? What happens to everything that falls in? Does it simply vanish, erased from existence? Or does nature have a more cunning plan, a secret vault where information is stored hidden from our prying eyes? Imagine throwing a book into a roaring furnace. The pages are consumed by flames, the words reduced to ashes. It seems as though the information contained within that book is irretrievably lost. But what if, somehow, every atom, every particle of smoke carried a faint echo of that book's content, a ghostly imprint of its stories and ideas? This is, in essence, the heart of the black hole information paradox, a conundrum that has plagued physicists for over 4 decades, a deep conflict between general relativity and quantum mechanics. At its core, the paradox asks a deceptively simple question: where does all the information that enters a black hole go? According to Einstein's general relativity, anything that crosses the event horizon, the point of no return, is doomed to be crushed into the singularity, a point of infinite density at the black hole's center. There, the laws of physics as we know them cease to exist. Information, like matter and energy, is seemingly obliterated, erased from the universe. But this poses a profound problem for quantum mechanics. One of the fundamental tenets of quantum theory is that information cannot be destroyed. Quantum mechanics is a deterministic theory. In principle, you should always be able to reconstruct the past from the present. If information is lost in a black hole, it would violate this fundamental principle, undermining the very foundation of quantum mechanics. This conflict was brought into sharp focus by the brilliant Stephen Hawking in the 1970s. Hawking demonstrated that black holes are not entirely black, but rather emit a faint glow of radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon, and it causes black holes to slowly evaporate over time. But here's the rub. Hawking radiation appears to be completely random, thermal radiation, carrying no information about what fell into the black hole. As the black hole evaporates, it seems to take all the information with it, leaving nothing behind. This is the information paradox in its starkest form. General relativity says information is destroyed. Quantum mechanics says it cannot be. Something has to give. So, how do we resolve this cosmic contradiction? Physicists have proposed a number of ingenious solutions, each more mind-bending than the last. One possibility is that the information is not actually destroyed, but is somehow encoded in the Hawking radiation. It's like trying to reconstruct a shattered vase from the fragments. The pieces are all there, but you need to know how to put them back together. The challenge is to find a mechanism that allows the Hawking radiation to carry information about the black hole's interior. One idea is that the correlations between the outgoing Hawking particles are far more complex than previously thought, encoding the information in subtle, intricate patterns. Another proposal suggests that the information is stored on the surface of the black hole, on the event horizon itself. This is related to the holographic principle, the mind-bending idea that all the information contained within a volume of space can be represented on its boundary surface like a hologram. Perhaps the event horizon is not a smooth, featureless surface as described by general relativity, but rather a complex quantum structure that stores all the information about the black hole's interior. It's like finding a hidden message etched onto the surface of a seemingly ordinary object. However, some physicists have proposed more radical solutions, challenging our very understanding of black holes. One such idea is the firewall proposal, which suggests that the event horizon is not a gentle crossing, but rather a violent inferno, a wall of energy that incinerates anything that tries to enter. This firewall would preserve information by destroying anything that carries it, but it would also violate Einstein's equivalence principle, the idea that gravity is indistinguishable from acceleration. It is a choice of which fundamental law to break in order to solve the paradox. Another possibility is the fuzzball proposal, which suggests that black holes are not singularities surrounded by event horizons, but rather fuzzy quantum objects with no well-defined surface. These fuzzballs would be made of tangled strings or other exotic forms of matter, and they would store information in their complex internal structure. Perhaps the black hole is not a bottomless pit of doom, but rather a highly complex library, storing information in a way that we do not yet understand. Solving the information paradox is not just about understanding black holes. It's about understanding the fundamental nature of reality. It's a crucial consistency check for any quantum gravity theory. This is just another stop along the way, and may need to revisit some ideas. If we revisit some of these ideas, could it be that space and time are not fundamental entities at all, but rather emerge from something deeper, something more fundamental? So if we revisit some of these ideas, could it be that space and time are not fundamental entities at all, but rather emerge from something deeper, something more fundamental? Is it possible that what we perceive as the immutable stage upon which the universe plays out its drama is actually an illusion? A construct born from something far more intricate and mysterious? Picture a vast ocean, seemingly boundless and continuous. Now imagine that ocean is not made of water but of countless tiny grains of sand, each grain interacting with its neighbors in a complex dance. From afar, the ocean appears smooth and continuous, but up close you see the discrete nature of its composition. This is, in essence, the radical idea behind emergent space-time, the notion that space and time themselves are not fundamental, but rather emerge from a deeper, underlying quantum reality. It is a concept that challenges our deepest intuitions about the nature of the universe and forces us to question the very fabric of existence. What if our familiar notions of location and duration are merely approximations? Convenient fictions that work well at large scales but break down at the Planck scale, where quantum gravity reigns supreme. What if space and time are not the fundamental building blocks of reality, but rather the result of some deeper, more fundamental processes? Think about a rainbow. It appears to be a distinct object, a colorful arc hanging in the sky. But in reality, it is not a physical object at all. It is an emergent phenomenon, created by the interaction of sunlight and raindrops. The rainbow exists only because of the underlying physics of light and water. It is not a fundamental entity in itself. Could space and time be similar, emergent phenomena arising from something deeper and more fundamental? One of the most intriguing possibilities is that quantum entanglement, that spooky action at a distance we discussed earlier, could play a key role in weaving the fabric of space-time. Imagine a vast network of entangled particles interconnected across the universe by instantaneous links.
These links, these quantum correlations, could be the threads that stitch together the fabric of spacetime, creating the illusion of a smooth, continuous geometry. It is like a spiderweb spun from countless threads of quantum entanglement. Each thread connects 2 points in space, and the overall network creates a structure that we perceive as spacetime. The more entangled the particles, the stronger the fabric of spacetime becomes. Another intriguing idea is that information networks could be the foundation of reality. Imagine the universe as a giant computer, processing information at the most fundamental level. Each bit of information, each quantum bit or qubit, is linked to other qubits in a complex network. These connections, these information pathways, could define the geometry of spacetime. The more interconnected the qubits, the more complex the network, and the more structured the spacetime becomes. It's like a social network where connections between people define the structure of society. In this view, space is not just empty void, but a network of relationships. This idea connects naturally with the holographic principle, that mind-bending concept that suggests our three-dimensional reality could be merely a projection from a lower-dimensional surface. If the universe is a hologram, then all the information about our three-dimensional world is encoded on a two-dimensional boundary. The geometry of spacetime, the distances between objects, and the passage of time could all be encoded in the patterns of information on this boundary. It's like a movie that we are watching but does not quite have the full picture. Emergent spacetime is a radical concept that challenges our deepest assumptions about the nature of reality. If space and time are not fundamental, then what are they? And what is the underlying reality from which they emerge? These are questions that have no easy answers, but they are driving physicists and philosophers to explore new frontiers of knowledge. Is what we can see, feel, and experience truly everything that there is? Perhaps in the future we will discover that space and time are just illusions, convenient fictions that help us make sense of a far more complex and mysterious universe. Perhaps the true nature of reality is something we cannot even imagine, something that lies beyond the grasp of our current understanding. And is that all the questions we can ask about the fabric of reality? Are we truly grasping the cosmic story if our equations relentlessly crash against walls of infinity? Are those singularities, those points of infinite density at the hearts of black holes and the very beginning of time, nature's way of telling us we are missing something crucial? What if those infinitely dense points that we see from our math are actually like seeing something blurry and realizing it is really several things close together? They are not points, but objects that are beyond our current viewing resolution. For decades, Einstein's general relativity has painted a vivid picture of gravity, but it also leaves us stranded before these mathematical cliffs, unable to peer beyond. But what if quantum gravity offers us a way to smooth out those infinities, to round off those sharp edges, and to glimpse what lies beyond the event horizon or the moment of creation? Instead of an infinitely dense point, quantum gravity theories suggest that quantum effects step in to prevent matter from being crushed to an unimaginable degree. It is almost like a cosmic safety net. The density becomes extreme, yes, but finite, a state of matter and energy unlike anything we have ever witnessed. Think of it like squeezing a balloon. You can compress it so far, but eventually the rubber prevents you from squeezing it any further. What is in the balloon will eventually seep through a tear, then be compressed. But how does this smoothing process actually work? In loop quantum gravity, a leading contender for a theory of quantum gravity, space itself is not continuous but rather granular, composed of discrete units, quanta of space. There is a smallest possible volume, a limit to how small things can get. So, when matter is compressed to an extreme degree, it cannot simply be squeezed into an infinitely small point. It reaches a limit, a point where the quantum nature of space itself pushes back, preventing further collapse. This quantum pushback could have dramatic consequences, particularly for our understanding of the Big Bang. General relativity predicts that the universe began as a singularity, a point of infinite density and temperature.
But this singularity is problematic. It is a point where the laws of physics break down, where our understanding of the universe collapses. But what if quantum gravity can resolve this singularity, replacing it with something more palatable? What if, instead of a beginning, the Big Bang was actually a transition, a moment of cosmic bounce? This is the intriguing concept of the Big Bounce, an alternative to the universe's initial singularity offered by loop quantum gravity. Imagine the universe not as starting from an infinitely small point, but rather contracting from a previous state, squeezing down to an incredibly small volume, but never actually reaching a singularity. At this point of maximum compression, quantum effects kick in, preventing further collapse and causing the universe to bounce back, expanding outwards into the universe we see today. It would be as if our current expanding universe is just the latest phase in an endless cycle of expansion and contraction. A grand cosmic breath. This idea of a big bounce has some profound implications. It suggests that our universe may not have had a beginning, at least not in the traditional sense. It may have existed forever, cycling through phases of expansion and contraction, with each bounce marking a transition from one era to the next. Are we trapped in an infinite loop? What kind of universe would exist before ours? Perhaps there is a universe on the other side of the Big Bounce, a mirror image of our own, governed by different laws of physics. Or perhaps the Big Bounce is not a smooth, symmetrical transition, but a chaotic, unpredictable event, leading to a new universe with entirely different properties. Maybe it is like a lottery ticket that is won, but instead of money, a new universe is created. Could there be a way, perhaps through subtle patterns in the cosmic microwave background, to find proof of that previous universe? Or will we forever be trapped, unable to view what came before the Big Bounce? The Big Bounce is not just a theoretical concept. It has potential observational consequences. It could affect the distribution of galaxies in the universe, the properties of the cosmic microwave background, and even the nature of dark matter. Scientists are currently searching for these subtle signatures, hoping to find evidence that our universe did indeed bounce, rather than begin from a singularity. Are there any echoes of a previous existence still bouncing around? The fate of singularities, the smoothing out of infinity, and the possibility of a big bounce all point to a deeper, more nuanced understanding of the universe, one that transcends the limitations of general relativity and embraces the quantum nature of gravity. It is a quest to understand the ultimate origin of the universe, to unravel the mysteries of space and time, and to glimpse the very fabric of reality. And while singularities themselves may be tamed, there may be even more to question. What exactly makes up the very building blocks of reality? What is more fundamental than space and time? The scientific community may be just years from learning that everything we thought we knew was nothing more than an illusion. And while singularities themselves may be tamed, there may be even more to question. What exactly makes up the very building blocks of reality? What is more fundamental than space and time? The scientific community may be just years from learning that everything we thought we knew was nothing more than an illusion. But if all of our theories thus far, as stunning as they are, keep leading us to paradoxes, to questions we seemingly cannot answer, could it be that we are missing something even more fundamental? What if the solution requires us to not just refine our existing models, but to completely dismantle them? To start anew with concepts so radical they challenge the very fabric of logic itself. Imagine for a moment a master painter standing before a canvas, equipped with the finest brushes and the most vibrant colors. He skillfully recreates a breathtaking landscape, a scene so realistic it seems to breathe with life. But what if, upon closer inspection, we discover that the canvas itself is not what it seems? What if it is not a flat surface, but a complex, multi-dimensional structure, and the paints are not pigments, but something far more exotic, something we cannot even comprehend? This is the challenge facing physicists today. Are we truly seeing the universe for what it is, or are we merely interpreting a shadow of a far grander, far stranger reality? Perhaps, to truly understand quantum gravity, we need to move beyond the familiar frameworks of both relativity and quantum mechanics, to venture into uncharted territory where the very rules of the game are rewritten. What would such a revolution entail? It might require us to rethink our most fundamental assumptions about locality, the idea that objects can only be influenced by their immediate surroundings. Quantum entanglement already hints at a non-local universe, where particles can be connected across vast distances, seemingly defying the laws of classical physics. What if this non-locality is not just a quirk of the quantum world, but a fundamental property of reality? A sign that space and time are not as absolute as we thought. It might require us to question our understanding of causality, the principle that cause must precede effect. In the quantum world, time can become blurry, with particles seemingly traveling backwards in time. What if, at the Planck scale, causality breaks down altogether, with cause and effect becoming intertwined in a complex, nonlinear dance? Some physicists are even questioning the very nature of logic, suggesting that our familiar laws of reason may not apply at the most fundamental level. Imagine a universe where contradictions can coexist, where something can be both true and false at the same time. It sounds like nonsense, but some mathematical frameworks, such as paraconsistent logic, allow for such possibilities. Could this be the kind of logic that governs the quantum realm? Of course, venturing into such uncharted territory requires entirely new mathematical structures and physical principles. We may need to abandon our reliance on geometry, the language of general relativity, and embrace new forms of mathematics that can describe the quantum nature of space and time. Perhaps the answer lies in number theory. Imagine, instead of smooth geometry, a universe built from numbers, from abstract relationships between prime numbers. That seems far out of reach, yet what if that universe has a deeper level than quantum level? Perhaps we are on the precipice of a scientific revolution as profound as those initiated by Albert Einstein and Max Planck, a revolution that will reshape our entire worldview and inspire future generations to dream even bigger. There is the thought experiment of Schrödinger's cat, but what if the cat is the universe, and the box is our minds? Until someone opens it, there are endless states that the universe could be in, and the person opening the box is quantum gravity revealing itself. What wonders and horrors would be released? What if this whole time reality has been an unsolvable Rubik's Cube and quantum gravity is a hammer? It is a long shot, but what other choice does humanity have but to follow the science wherever it may lead? What if this whole time reality has been an unsolvable Rubik's Cube and quantum gravity is a hammer? It is a long shot, but what other choice does humanity have but to follow the science wherever it may lead? But even with a complete understanding of quantum gravity, would humanity truly understand reality? Or would we just have a really cool hammer? The pursuit of quantum gravity inevitably leads us to the doorstep of philosophy, forcing us to grapple with questions that have plagued thinkers for millennia. Is time a river, constantly flowing from past to future, or is it more like a still photograph, with all moments existing simultaneously? What exactly is time? Does it have a starting point? Does it even need to exist? Einstein's theories, for example, challenged our intuitive understanding of time, demonstrating that it is relative, not absolute. Time slows down for objects moving at high speeds and is warped by gravity. These effects, while seemingly subtle, have been confirmed by countless experiments and observations. The global positioning system satellites that guide our cars and planes must account for these relativistic effects to function accurately. But quantum mechanics throws another wrench into the works. In the quantum world, time becomes blurry, with particles sometimes seeming to travel backward in time. Cause and effect can become intertwined, challenging our linear perception of the universe. What if our idea of before and after is just a comforting lie? What if there are no starts and stops, just endless loops? The concept of the block universe,
suggests that all moments in time, past, present, and future, exist simultaneously in a four-dimensional block. Our experience of time flowing is merely an illusion, a trick of consciousness. It is as if we are passengers on a train, moving through a landscape that is already laid out before us. Do we even have free will in that version? This raises profound philosophical questions about free will, determinism, and the nature of consciousness. If all moments in time already exist, are we truly free to choose our actions, or are we simply following a predetermined path? If time is an illusion, what does that say about our sense of self, our memories, and our hopes for the future? Could what we call life be more like watching a movie than living it? Then there's the question of the ultimate beginning. Did the universe have a starting point, a moment of creation, or has it existed forever, cycling through endless phases of expansion and contraction, as we said before with the Big Bounce theory? If the universe did have a beginning, what caused it? What existed before the beginning? These are questions that have no easy answers, and they push us to the very limits of our understanding. Did someone turn the lights on in an empty room? Many cultures throughout history have grappled with these questions, offering a variety of creation myths and cosmological models. Some believe in a divine creator, a supreme being who brought the universe into existence. Others believe in a cyclical universe, constantly renewing itself through destruction and rebirth. Are those ancient cultures that created entire religions around those questions closer to the truth than our scientists? Quantum gravity, in its quest to unify general relativity and quantum mechanics, offers new perspectives on these age-old questions. By exploring the nature of space, time, and the universe at the most fundamental level, we may gain insights into the nature of reality itself. Perhaps we will discover that the universe is far stranger, far more mysterious, and far more wonderful than we ever imagined. Perhaps quantum gravity isn't just about solving equations, but it's also about finding our place in this vast and enigmatic cosmos. These theories challenge our deepest intuitions about reality, existence, and observability. If the holographic principle is true, and our three-dimensional reality is merely a projection from a lower dimensional surface, what does that say about the nature of existence? Are we real, or are we just shadows on a wall? Maybe it is all just a dream. And what does it mean to observe the universe? In quantum mechanics, the act of observation itself can alter the outcome of an experiment. Does this mean that our consciousness plays a fundamental role in shaping reality? Does the universe only exist because we are observing it? These questions, while seemingly abstract, have profound implications for our understanding of the universe and our place within it. They force us to confront the limits of our knowledge and to acknowledge the mysteries that still lie beyond our grasp. The intricate relationship between theoretical physics and metaphysical inquiry is about to be tested. Perhaps by working together, the answers will come faster. After all, many scientists through history have found inspiration in philosophy. Take Albert Einstein, for example, who was deeply influenced by the writings of philosophers like Immanuel Kant and Baruch Spinoza. Einstein's theories of relativity were not just the product of mathematical equations. They were also the result of deep philosophical reflection on the nature of space, time, and the universe. Without Spinoza, would we even have Einstein? Or consider the work of Niels Bohr, one of the founding fathers of quantum mechanics, who was heavily influenced by the philosophy of existentialism. Bohr's interpretation of quantum mechanics, known as the Copenhagen interpretation, emphasizes the role of the observer in shaping reality, a concept that resonates with existentialist themes of subjectivity and freedom. Perhaps without the understanding of great minds, science could not have moved forward. The search for quantum gravity is not just a scientific quest, it is a philosophical journey, a quest to understand the fundamental nature of reality and our place within it. It is a journey that will require us to challenge our deepest assumptions, to embrace new ideas, and to venture into uncharted territory. Are the things that we can touch all there is?
Or is there a deeper connection between things that we cannot comprehend? As we continue on this journey, we can be sure of one thing: the discoveries that await us will be nothing short of revolutionary. They may challenge our current understanding of the universe, but they will also open up new possibilities for knowledge, understanding, and perhaps even a new appreciation for the grand cosmic drama in which we are all players. And the cast of characters is vast, and the stage is even bigger, and some wonder if it is too big to be alone. Is there an audience out there somewhere watching us? As we continue our exploration of these grand concepts and struggle to define the most foundational aspects of our universe, what if there is more than just one universe? What if ours is just one bubble floating among countless others in an endless cosmic sea? The idea of a multiverse, a universe of universes, might sound like pure science fiction, something straight out of a Philip K. Dick novel or an episode of Star Trek. But this concept is a very real possibility within certain frameworks of quantum gravity, particularly string theory and the theory of eternal inflation. Are we the sole inhabitants of reality, or do we have countless cosmic neighbors? To understand why the multiverse arises in these theories, it is like venturing down a rabbit hole and venturing through our math to see if it is possible to be correct. String theory, with its extra dimensions, opens up the possibility of different universes existing on different branes, those higher dimensional membranes floating in a larger bulk space. Each brane could have its own unique set of physical laws, its own constants of nature, its own particles and forces. It is as if the cosmos is one giant condo building, but we can only see our condo. Imagine a vast ocean filled with countless bubbles. Each bubble represents a universe with its own unique properties. Some bubbles might be small and short-lived, quickly collapsing back into nothingness. Others might be large and stable, capable of supporting life. And still others might be so different from our own that they are virtually unrecognizable. They would be a universe, but just not the kind that we would be able to observe or live in. Then there is the theory of eternal inflation, which suggests that the universe underwent a period of incredibly rapid expansion in the first tiny fraction of a second after the Big Bang. According to this theory, inflation is not a one-time event, but rather an ongoing process that continues to this day in some regions of space. It is like saying that the Big Bang never stopped, it just kept going. As inflation continues, it spawns off new bubble universes, each with its own unique properties. These bubbles are constantly popping into existence, creating an endless multiverse of possibilities. The mind-boggling thing is how we just keep finding new concepts. Each time one thing leads to another, it would be almost like the universe wants us to learn about it. It has already been 13.8 billion years. What would it hurt if we took another billion years to learn it? What if each universe is a cosmic lottery ticket, with a random set of physical laws determining its fate? Most of these universes would be sterile and lifeless, unable to support the formation of stars, galaxies, or planets. Only a tiny fraction of these universes would have the right conditions for life to arise. Is that the fate of our universe as well? A lottery that we are just waiting to lose? This leads to the anthropic principle, which states that we observe the universe to be the way it is because if it were any different, we would not be here to observe it. In other words, we live in a universe that is compatible with our own existence. And that may be a cosmic accident, a stroke of unbelievable luck in the face of impossible odds. In this multiverse picture, our universe is not unique, but simply one of countless others, each with its own set of physical laws. We just happen to be living in one of the rare universes that can support life. But is the multiverse a testable scientific hypothesis, or is it merely a philosophical speculation? This is a question that has divided physicists for years. Some argue that the multiverse is inherently untestable because we can never directly observe other universes. They are beyond our cosmic horizon, forever hidden from our view. It would be almost like saying we have all the pieces to the puzzle except we can't find the other puzzle. Others argue that there may be indirect ways to test the multiverse hypothesis. For example, if our universe collided with another bubble universe in the past, it could have left subtle imprints on the cosmic microwave background, the afterglow of the Big Bang. It is almost like a fingerprint showing us what happened. Scientists are actively searching for these imprints, hoping to find evidence of a past collision. That cosmic microwave background may hold more secrets than we realize, and there are other possibilities. Perhaps the existence of dark matter or dark energy can be explained by the influence of other universes. Or perhaps the values of the fundamental constants of nature are not arbitrary, but are determined by the properties of the multiverse as a whole. Those questions may also lead us to more questions. It would be almost as if the universe knew that we would try to solve the mystery by any means possible. The multiverse raises profound questions about our place in the cosmos. If our universe is just one of many, does that diminish our significance? Are we just a random accident in an endless sea of possibilities? Or does the existence of the multiverse make our existence even more precious, even more remarkable? We could be the only ones around for all we know. Think of it like this. If you have one painting in a gallery and it is the only one, is it more precious because of its uniqueness, or is it less so because it has no one to appreciate it? Some argue that the multiverse diminishes our uniqueness, making us just one of countless others. But others argue that it enhances our uniqueness, making us a rare and precious gem in an endless sea of possibilities. Regardless of your perspective, the multiverse is a concept that forces us to confront our place in the universe and to question the very nature of reality. Is what we can see, touch, and feel truly all there is? What other realms are out there? Perhaps the answer isn't to look for it, but maybe to create the lens to see it. We may be getting closer and closer, but still so far away. The exploration of the multiverse is a testament to human curiosity, our unwavering desire to understand the universe and our place within it. It is a journey that will take us to the very edge of knowledge, and beyond, and maybe to the edge of what we ever knew could exist. But if the key to understanding our existence lies in the echoes of other universes, we must consider that those answers are likely not going to be clear or easy to grasp. No matter what, the answers may not be able to be found. After all, we will only find them if we look, and that is all we can really ask for. So if the key to understanding our existence lies in the echoes of other universes, we must consider that those answers are likely not going to be clear or easy to grasp. No matter what, the answers may not be able to be found. After all, we will only find them if we look, and that is all we can really ask for. But where do we go from here? What is the road ahead for quantum gravity research, and what can we expect from those working on it? We have explored the theoretical landscape, a terrain dotted with ambitious ideas. String theory proposes vibrating strings in extra dimensions, while loop quantum gravity weaves spacetime from interconnected loops. Each approach offers a unique perspective, a different set of mathematical tools to tackle this ultimate challenge. But the question remains which, if any, of these paths will lead us to our goal. The simple truth is that we are at an interesting impasse. For all their ingenuity, these theories remain largely unverified. They are beautiful mathematical frameworks, yes, but lack the crucial stamp of approval from the real world, experimental evidence. It is as if we have constructed elaborate maps of a distant land without ever setting foot on its shores. And this is where the challenge lies. We have discussed many ways to test and retest theories that have not yet been proven. We require something to measure that we cannot currently measure with the tools we have. What happens now? That is why the next breakthrough will not come from theory alone. We have reached a point where further progress demands a closer engagement with the experimental realm. We need new observations, new experiments to guide our theoretical efforts, to separate the promising ideas from the dead ends. We need nature to give us a nudge, a subtle hint, to point us in the right direction. The experimental challenge is formidable.
We are talking about probing the Planck scale, a realm of unimaginable smallness and energy. This is a realm so far out of reach. Some have said that we will never measure it, but we need to at least attempt to reach it. This is not just a matter of building bigger colliders or more sensitive telescopes. It requires a new level of ingenuity, a new way of thinking about how we can extract information from the quantum gravity realm. Consider the cosmic microwave background, the afterglow of the Big Bang. Scientists are not just looking for average temperatures, but tiny, subtle patterns that might betray the presence of quantum gravity effects. Or there's the search for gravitational waves, those ripples in space-time predicted by Einstein, as well as the new and crazy idea of space-time. These tests, no matter how sophisticated, are not simple experiments. They take vast collaborations across the globe. Scientists must work together with resources coming from everywhere. It is only with a combined effort can these ideas move forward. It is not some lone scientist sitting in a lab figuring everything out themselves. It requires people, nations, and the best and brightest to explore this new frontier. This is no longer the domain of a few isolated geniuses. It is a global scientific adventure, driven by the collective creativity and persistence of thousands of researchers around the world. From the halls of academia to the high-tech laboratories of government and private institutions, this new generation of scientists is building off the work of the past. It is in the scientific spirit of discovery. It is about moving science forward. The scientific process needs scientists and engineers to work with theorists and mathematicians. They all must come together for humanity to better understand its place in the universe. This collaborative spirit is perhaps our greatest asset in the quest for quantum gravity. It is the engine that drives innovation, the catalyst that sparks new ideas, the glue that holds this grand scientific endeavor together. There's an intrinsic value in the pursuit of knowledge, a deep human desire to understand the universe and our place within it. It is this fundamental drive that fuels the scientific process, that inspires us to push the boundaries of what we know. But it is not about the individual. There may be people that want to get the credit and fame that may come from it, but it is something much greater. It is an effort that touches the human spirit. It will change the world, it will change humanity, it will change us. It is in our very nature as humans. It is not about what we get from it, but what we do. In the pursuit of quantum gravity, we are not just seeking to solve a scientific problem, we are seeking to understand the fundamental nature of reality itself. We are questioning our deepest assumptions about space, time, and the universe, and in doing so we are pushing the boundaries of human thought. What, then, will the future of the search of quantum gravity look like? The road ahead is filled with challenges, no doubt. There will be setbacks, detours, and perhaps even moments of doubt. But there will also be moments of exhilaration, moments of insight, and perhaps even moments of profound discovery. The quest may be arduous, and the destination uncertain, but the journey itself is a testament to the power of human curiosity and the unwavering spirit of scientific inquiry. Is it not worth all the effort if we could know everything there is? The exploration continues. Imagine, if you will, two towering figures, Albert Einstein and the pioneers of quantum mechanics, each revolutionaries in their own right. Their genius forever altered our understanding of the cosmos, yet their triumphs also revealed a profound cosmic conflict. It is a battle of titans where gravity as we see it and the quantum world seemingly cannot occupy the same space. Their legacies are not endpoints, but rather launch pads, propelling us toward a future where this conflict is finally resolved. And the potential rewards, well, they are nothing short of a complete reshaping of our worldview. The revolutions instigated by Einstein and the quantum pioneers are far from over. Indeed, one might argue that they have just begun. The quest for quantum gravity is nothing less than the completion of their unfinished work. We strive to reconcile their seemingly incompatible visions, the elegant curvature of space-time with the probabilistic fuzziness of the quantum realm, to weave these threads together into a single coherent tapestry that reveals the universe's fundamental laws.
Think about it this way. Einstein gave us a new lens through which to view the cosmos at its grandest scales, revealing the secrets of gravity, black holes, and the expansion of the universe. The quantum pioneers, on the other hand, opened up a window into the infinitesimally small, unlocking the mysteries of atoms, particles, and the forces that govern their interactions. But these two lenses, while incredibly powerful, are not yet aligned. There still might need to be a new lens created. The search for quantum gravity is then an attempt to build a single unified lens, one that can focus on both the largest and smallest scales simultaneously, revealing the true nature of reality at its most fundamental level. It is the journey towards a theory of everything, and this ultimate theory is more than just a set of equations, more than a collection of abstract mathematical concepts. This is the promise of a profound shift in our understanding of what it means to exist, to be conscious, to be a part of this vast and enigmatic cosmos. The ramifications of a successful theory would ripple far beyond the confines of physics, impacting fields such as philosophy, cosmology, and even our understanding of consciousness itself. Imagine a world where the secrets of the Big Bang are finally revealed, where the mysteries of black holes are laid bare, where we can manipulate gravity with the same precision as we manipulate electromagnetism. The possibilities are boundless, limited only by our imagination. The development of new technologies and materials that could transform society, the creation of new forms of energy, a deeper understanding of the origins and evolution of life. Think of the advances in technology that came from splitting the atom. No one could have foreseen the possibilities. Quantum gravity will offer those same possibilities and more. The quest for quantum gravity is then not just a scientific endeavor. It is a testament to the enduring power of human curiosity, our unwavering desire to explore the unknown, and our unyielding belief that we can unravel the mysteries of the universe. The work that we are doing today is not for us, but for our children's children. It is humanity's legacy. So, as we stand at this pivotal moment in scientific history, let us embrace the challenge. Let us celebrate the achievements of those who came before us, and let us look forward with awe and anticipation to the discoveries yet to come. The universe is vast and mysterious, but it is not beyond our grasp. The journey will be long and arduous, but the destination is worth the effort. For at the end of the road lies the ultimate prize, a complete and unified understanding of the universe and our place within it, and the secrets of our universe have just begun to be unraveled. What wonders await us, what incredible possibilities will be unveiled, what other mysteries are out there in the vast cosmos waiting to be discovered.